in a material called semiconductor, which was known to the physicists earlier, but not a material for practical application till then. It is at the time 47 I have written. It was really the 47 to 15, that period, which was very jubilant, very interesting period, when there was a tremendous it was a revolutionary period in the history of electronics. In the history of electronics, it was a revolution. Transistor was discovered. Ultimately, the three scientists, they got Nobel Prize for that. And the first device was made in a material, not silicon, which is so popular today, but in germanium. It was a point contact device, but it has tremendous potential. It started with that. Miniaturization of electronics started with that. It had all the properties of a triode or pentode, but with a much lower voltage, 10, 15, 30 volts, those days, with a much lower power consumption, 1 watt or less, and much smaller space, maybe 1/10 to 1/100th of those days electronics. You have seen perhaps in your house, some of your family, you have big radio sets, which is now no longer in use. And thereafter, research focus totally was on the miniaturization, further and further miniaturization, and the material silicon, due to various reasons, became much more practically important than germanium, because of various, we are not discussing all those critical issues here. And a technology called silicon planar technology came, and that started in 1950s. That started, you can see, I can afterwards show you silicon planar technology indeed in 50s, and it led to integrated circuits. You know, the Jack Kilby was awarded Nobel Prize after 30 years for that basic invention, which revolutionized the world. The world today, our life cannot sustain without a microchip, microprocessors, and various other things. Okay? So integrated circuits started developing and growing rapidly during 60s, and we shall be discussing that there was a competition between two kinds of devices, one called bipolar devices, the other called MOSFETs. Ultimately, MOSFET gained more momentum because of various reasons, and VLSI concept, LSI-VLSI concept came, and it led to a system on a chip called SoC. Simultaneously, along with that, you can see the slide, simultaneously along with that, it was found that the technology used in microelectronics also could be used into microfabricate three-dimensional microstructures on materials like silicon, which was earlier thought is an electronic material. Afterward, it was found it is a very good mechanical material too. So there was a new kind of technology started evolving. That is just the focus of this particular workshop, Microsystems or MEMS, and it started with micro machining, borrowed from microelectronics technology, and MEMS came up and started flourishing. We shall be discussing that afterward in detail. We shall now quickly go, because our MEMS, after half an hour we shall switch to MEMS. Already 5 minutes have passed. As all of you know that the technology to how transistor, from transistor to today's VLSI, ELSI system on chip concept came, it came through various phases. I said valves. Valve is obsolete today, but mainly important thing is PCB. PCB technology was started from printed circuit board, from printing technology, lithography and other things, photolithography and silicon planar technology. photolithography and silicon planar technology. Linear, I told you about bipolar ICs. These things, as you all of you know. This is very device continuously there was a shrinking of device dimensions, making it smaller and smaller. Chip size started increasing because one tried to incorporate a full system on a chip. Speed and power dissipation. Speed has to be increased, power dissipation has to be reduced, and power delay product is a very important parameter. Microprocessors, CPUs, etc., DSP chips. On chip analog, this was another very serious thing. This is another very serious thing because mostly what we do is analog functions. You collect a signal from a voice. It is an analog signal, but you would want to do various processing on it. Earlier it was entirely analog. Digital was not developed, but thereafter things changed because of various reasons, as you know. Already you have gone through those courses. And you know that analog signal is the starting. Analog signal again at the end is the magnified version is also very important, but intermediately it has to be processed through digital means, and it is important to integrate analog functions and digital functions on the same chip to make it cost effective and simple and attractive commercially, and that is very important. On chip analog digital functions and bipolar and MOS technology is integrated on the same chip, BiMOS it is called, and ultimately, as you know, the world is tending towards nano. Everybody is speaking of nano. Some people call it nanomania, and those who are totally exaggerated by that, and they call it nanophobia. Some people are saying nano. We are very happy to make it finally to declare I have made it a nano. It has practically, frankly speaking, the microelectronics truly has become a nano system, because today's microelectronics, the devices are extremely small. Their dimensions in the range of nanometers. It is not chemically and arbitrarily done. It is done all by structured manufacturing technology. And today, therefore, today's ICs, they are called nanoscale MOS, some called nano CMOS. So this is the trend which has taken place over the years. And it was guided by somebody very famous, Gordon Moore. He predicted in 1965 that they were real visionaries. Gordon Moore, co-founder of Intel Corporation. He predicted that the chips, this capacity will enhance twice, by a factor of 2 every 2 years or every 1.5 years. Chip size the device size will shrink, chip size will increase, and like this, capacity, speed, power, etc. All points of view, the improvement will take place by a factor of 2 every 1.5 years to 2 years. And that trend was going on till 2005 very well. You see, it is a log scale plot. I will give you another plot afterward. It's called Moore's plot. It is a semi-log. These are years. This is years. These are years of development, and this is the number of components per chip, number of transistors per chip. There is a straight line. It means it is semi-log. Means it is logarithmic increase, exponential rise, and this is a phenomenal development. And in this respect, I would like to say, because we are one of the, as rightly pointed out Dr. Nayak, that we are one of the few institutes in this country who got involved in microelectronics, MEMS, and integrated optics business from 80s onward. Okay, so I will try to give you a few slides on what happened in IIT Kharagpur over the years since the end of 80s till today. Till today, I do not have information much for the last 3-4 years. Before that, I have more or less some information. I will try to. And here I mention some of the important developments which took place in our laboratory, which developed a silicon technology lab, silicon processing technology lab for bipolar ICs, started with telecard and various other things. And one of the most important things for ISRO here is relay driver chip for satellites. Relay driver chips for pure microelectronics thing. However, we did a lot of work for other people also. And that's how we gradually got into the business of microelectronics in a lab, completely fabricated by without going to anybody. Even chip mass fabrication was done here. Some of the diagrams, some of the pictures of the lab those days. Here I show one gentleman. Many of whom you know him probably, Professor S. Call, who was my junior colleague, very closely involved in all programs, but he just at a very young age he expired, and that was an irreparable loss for the department and for the activity of IIT Kharagpur. And here showmen you can see and others are some of the facilities of the lab. You can look at it. And these are some of the chips which were made in IIT Kharagpur using our own facilities. Some small micrographs of those chips. You can have a look. ECL chip, emitter coupled logic, you know about it. It is the fastest with the same feature size. It is the fastest logic including all bipolar and MOS logic families. Ultimately, it is high power consuming, unfortunately. So its use is very limited. Only in very special applications, space and others, ECL is still being used. But we developed for the first time in the country analog multiplier chip on a linear bipolar array, which was developed in the lab, which was taken over finally by Bell. ASIC relay driver chip, I talked about the thing which he made for Mr. Goel of ISRO SACS. It is called Isaac. And Professor Das is just sitting here. His research topic was on a topic called ion beam sputtered polysilicon film. This was developed by this kind of polysilicon resistor was developed by Professor Somen Das in the lab, and he made a lot of investigations on it in his PhD on high current pulse streaming, etc. And this is one interesting work by Dr. Somen Das. Sorry. একটা কোন দিক দিয়ে করে জানা This is very interesting. I think we don't have time to discuss this thing, so just quickly bypass it. But this is important. This is called polysilicon fuse. You know, just like our fuses which we use in our homes, in the microcircuits also we make use of small fuses for customizing a chip. There are two kinds of fuse. One is called anti-fuse. Anti-fuse means a fuse which becomes open circuit after application of voltage, and fuse links which becomes a short circuit after application of a current. This is a fuse link developed in the lab, and Professor Das made a investigation on how the fuse behaves, how its resistance changes with time before and he made some physical investigations on that. You can have a look before. Here you can see this thing better in this plasma TV. You see that just before fusion, how it looks like. It melts like through a channel at the center of the polyresistor. Now, this was the story of IIT Kharagpur, but IIT Kharagpur had to stop somewhere because of limited facilities. We could not make a device with dimensions less than few microns. But technologies did not stop here. All over the world, there was tremendous effort, and companies like Intel, they are the pioneer in making things smaller and smaller. And you know Intel, all these chips today, Intel is pioneer. There are many other big companies, but Intel is pioneer in microfabrication of chips. And I have given you some story about how the things changed during the past three decades, and how things have gone from micro dimensions to nano dimensions over the years. I do not want to repeat that here. And here the story of scaling comes. Scaling means making dimensions smaller or improving the properties. For example, gate oxide thickness scaling, first off. You know, for the MOSFETs, most important parameter is the gate. It is a field effect device. It does not draw any DC current. At the gate, current is zero. DC current is zero. Only during transients there is a current because of the capacitances. Okay? And that is the asset of MOSFET, that you can make devices which are called dynamic devices. Dynamic ROMs, DROMs, CD-ROMs, and then you can make dynamic logic also, which is not possible in bipolar. Bipolar cannot keep a voltage for a long time because it is current operated, it is voltage operated. And the gate oxide, if gate oxide becomes leaky, this property is lost. And as you are reducing the dimension, gate oxide becomes thinner and thinner. It becomes leaky. How to prevent that leak, keeping the dimension small, is a challenge. And that was very well investigated by physicists and technologists all over the world and chemists all over the world. And you know, the revolutions have taken place. Leader is Intel. Junction scaling, making junctions smaller, both length and breadth, as well as in the depth. And VCC scaling is very important. VCC or VDD in this case, drain supply voltage. If you reduce it, then power distribution gets reduced by twice. VD is proportional to VDD squared. So reducing the VCC is a very good. Then threshold voltage is reduced. Many other issues are there, and that gradually, came into the picture. And there was a tremendous investigation. And 1990 is the golden era of scaling all over the world, and these three scaling factors became very important. Here, in fact, again Moore's law curve, and here it shows until 1985 up to 2005. It's called traditional scaling era. More or less the same technology being followed with shrinking dimensions. Additional technology, innovation was not that much, but after 2005. There were tremendous technological innovations. And Intel, again, let me tell you, they were the key player in that particular area. Key player. And because of lack of time, I cannot go into details. One important thing is, I think all of you, from your common sense, you understand. Now, you know that people are speaking of now CMOS with gate length, channel length of the order of 22 nanometer. 22 nanometer means 220 angstrom. 20 nanometer, 200 angstrom. It is an extremely small dimension. Ultraviolet light wavelength is typically 2050 to 300 nanometer. So 22 nanometer, you understand how small it is. Much smaller than a virus. Okay. So today's advanced CMOS technology, their minimum feature size is 22 nanometer, 45 nanometer, 65 nanometer, in that dimension. And then gate oxide is so small that the gate oxide is no longer a continuous film. It is scattered atoms. There we have called it gate oxide running out of atoms. That the so-called technical technologists in Intel used to describe it like this: getting out of atoms. Okay, very thin, scattered atoms, and then there are many physical problems, mainly the tunneling current. Here you see that here I show some region which is above 100 ampere per centimeter square, where tunneling, it is almost fully tunneling. one has to keep itself within that limit. This is for nitrided silicon dioxide, this is for silicon dioxide, nitrided is better. But this is a challenge. This is a challenge, let me tell you, this is a challenge. And then, so we have talked about the traditional scaling for a few minutes. I cannot give much time on it. My topic is again to MEMS. I have to switch over to MEMS after 5 minutes. Traditional scaling, I have all quickly covered. Then post-traditional scaling, beyond 2005, what started happening. And then two factors became very, very important. One is the PMOS. PMOS, as you know, the hole mobility is much less than the electron mobility. It is speedier, less speedier, and you have to do something for W by L ratio control. But that unnecessarily consumes area. So if you can improve the mobility of holes in the PMOS, there will be a great gain. Similarly, as you reduce the NMOS size, also there are various scattering events which dominate. That reduces mobility. You have to do something to work on that. That was a challenge. It's called mobility booster. It can be shown. If the silicon has a uniaxial strain, which is compressible in nature, hole mobility improves. And if silicon has a uniaxial strain, which is tensile in nature, electron mobility improves. So if you can do something, so that automatically there are in certain regions of silicon, compressible strain is produced, longitudinal strain is produced. You can have a PMOS there with higher hole mobility. You can produce some regions where the silicon has a tensile strain, uniaxial, and can locate NMOS there, the electron mobility enhance. And that lot of physics investigations were there. And in 90 nanometer technology, first Intel introduced some methodology which later was used by everybody. Then is poly depletion elimination. Polysilicon gate is popular for various reasons. And polysilicon being a semiconductor, when you apply gate bias, it gets depleting. And depletion of polysilicon increases the effective oxide thickness of the gate, that increases the threshold voltage. So you have to do something, either you replace polysilicon or do something. And people started use once again metal gate. Another thing is, I talked about the very leaky oxide, gate oxide getting leaky, tunneling. So what I can do? I can do something whereas effective oxide thickness is higher. Physically the thickness of the insulator is higher so that the tunneling is reduced, but effectively the oxide thickness is less. So what you can do for that? If you can use a high dielectric constant material in place of silicon dioxide, then effectively you can have a reduced thickness, but physically the thickness is more, so the tunneling is reduced. It's called high K dielectric. HIK means high K dielectric concept. And then future challenges. You can have a say that how this is important. This is important that this channel region of silicon in the PMOS has a compressible uniaxial strain. It is done by silicon germanium epitaxial deposition on the source drain side, and it's because of the bulk expansion of silicon germanium, the region in between the channel gets compressed, and it is a uniaxial strain. As a result, the hole mobility in this region is improved, and as a result, such PMOS works better than ordinary PMOS. However, for NMOS, what people do is on the polysilicon, they deposit a nitride. And this deposited nitride on polysilicon produces a tensile strain. This is because of the dissimilar, and this is a metallurgical thing. And this effectively enhances the tends it. That means that tensile force is created over this region, and as a result, the electron mobility here is more than the normal without the nitride silicon. Silicon nitride stress layer it is called. This is the technology for NMOS. So PMOS with this kind of technology, and NMOS with this kind of technology. So let us not go into the two. We have very less time. A typical picture of it is called scanning tunneling microscopic picture of sorry. এটা বড় অসুবিধা হয় আমার কি হলো উল্টো দিকে নিয়ে যাচ্ছে না ঠিক আছে চলে যাচ্ছে কি হচ্ছে এটা দেখো তো এটা আনতে চাই Oh, I was showing this. Sorry, I'm sorry. This is interesting. That is why I wanted to show you this particular slide. This is the scanning tunneling microscope study of a typical MOSFET in the nanometric region. This is gate electrode. This in this case is a polysilicon kind of thing material. It could be metal also. Tungsten is quite often used. Only 1.1 nanometer silicon dioxide. How scattered? You have seen the oxide. The molecules are random, and it is very its structure is not perfect. And the silicon substrate is a crystalline substrate. How ordered the atoms? Have you seen it? Crystalline substrate. All the atoms are beautifully ordered. Only at the interface there is a disordering. So this is an interesting picture. That is why I showed you. I am not going into the details of these things. You know that this is a picture which may be of interest to you. How the 45 nanometer microprocessor products from Intel look like in dimension, proportionate dimension, single core, dual core, quad, 6 core, 8 core, etc. 45 nanometer is a very standard technology all over the world. 20 nanometer is upcoming, but it will be replaced by still smaller dimensions in the near future. I do not know what is the status of things in SCL. Professor Nayak Metal, what is the situation in SCL now? 0.18 it is now functioning. Good. So in our country also, we are not sitting idle. In the government level, there is an effort by the earlier Department of Electronics and afterward by ISRO. The Chandigarh plant has been renovated, and it is coming up with a 0.18 or 0.13 micron type technology. It is getting, and Professor Nayak is still involved with that very much. I am a member of that society. Sometimes being called, but I cannot attend all the meetings. But otherwise, India lags behind very much, let me tell you. And very few countries can compete. Very few countries. It is in the monopoly of a few in the world. And top among them is Intel. They have plants in certain regions. In Israel, there is a plant. And maybe they are saying that they will be setting up a plant in somewhere in our locality. Noida, it is coming up. Okay, so I have to stop somewhere this thing. There are so many other things. I cannot otherwise start my next talk. Before concluding, let me tell you something, that people are not sitting idle. As you are getting shrinking, as you are making smaller and smaller, silicon technology, it may appear that it will gradually lose its validity. Because MOSFET will not work as MOSFET. Quantum concepts have to bring in. And that is why people are all now trying into the other avenues, going into the other avenues, using quantum mechanical concept directly in silicon technology and in general into semiconductor technology. And various things have happened today. We have heard of quantum structures like quantum wells, quantum wires, quantum dots, etc. They are being in carbon nanotubes, silicon nanotubes. These are all quantum structures, and they are being investigated in detail. But technologically, let me tell you, commercially, to come to the level of silicon technology, it will take maybe another 10 years or 15 years. I do not know how long. Silicon technology is so mature. Let me tell you, 20 nanometer technology is not a matter of joke. All nanostructures which you speak of by the material science people, their dimensions vary from 5 nanometer to 100 nanometer. And this is 20 nanometer is the physical horizontal dimension. Small features inside is sub-nanometer. And people are making them, and very regularly and with a very high yield. That is the technological status today. So to compare with that by the other avenues is not easy. It will take time. Thank you very much. I'll go to the next topic. মেমসটা কোথায় ছিল জানো? গার্ড করলে তোমরা একজন এসে, তো মেমসটা কোথায় আছে দেখো তো। এইটা কি? ঠিক আছে, এইটা ঠিক আছে, ঠিক আছে, ঠিক আছে, ঠিক আছে, এটা পেয়ে গেছে। I told you that MEMS technology is a child born out of microelectronics technology. So already I have mentioned about it. So I repeat the same structure, picture, same slide where it shows at the end there are two divisions from integrated circuit technology developed in 60s. One side was the continuous development of VLSI system on chip, etc. Other side was micro machining and MEMS and microsystem. In Europe, MEMS is not preferred. People used to call it microsystems. Whereas in America, USA, and the rest of the world, MEMS is a very popular technology. They are the same. Because our workshop is on MEMS basically, I should mention a few things about micro machining, MEMS, and microsystems evolution in the beginning of the technology. You know, the discovery of strong piezoresistive effects in silicon and germanium in 1954 by Smith was a prime mover, very important thing in MEMS technology. A resistor in a microstructure, resistor means resistance, dope resistor in a microstructure fashion. If it is under pressure, if it is stressed, its resistivity changes quite differently, quite sensitively compared to strain gauge, metal strain gauges. There are reasons behind it. This was an important aspect why MEMS became a dominant technology in the very beginning. In 1954, you see that this is an important paper. Then photolithography and etching recognized as a tool for micromachining. Earlier, the mechanical engineer, they did not believe in this kind of thing. They believed in lathe, milling, and all these machines. And miniaturization of very small. So you have seen that probably some of you in the Bell in Bangalore and some other places. You have seen watchmakers lathe. Very small, tiny versions, robotic versions of various things are coming up. But it was found that if micromachining technology borrowed from photolithography and microelectronics fabrication is used, At the same time, you can produce hundreds and thousands of products simultaneously, called batch processing. That advantage is not there in conventional machining process in mechanical engineering. Though you can make very small, tiny products, but it's very difficult to make thousands of devices quickly. Batch processing. Silicon was established an excellent mechanical material by a pioneering paper by Peterson in 1982 in Proceeding Scientific. This paper discusses in detail about the properties of silicon, not only electronics, but electronic properties are well known, mechanical properties of silicon. He found that it is as good as, maybe better than stainless steel in several aspects. And it could be processed very easily by fabricated in microstructure form by and then ultimately after this paper, there is a mushrooming growth of MEMS industries in Silicon Valley, along with ICs, along with the traditional chips, microchips, both that was Silicon Valley mostly was a design area, but there was many plants at that time for making chips also. That shifted to various other parts of the world slowly. But it started with that. But then MEMS became a dominant field. And in fact, there was a time when we started our MEMS activity in IIT Kharagpur, we had an observation, the lab we created may not be suitable for microelectronics, but very suitable for MEMS. And we started, but thereafter MEMS also, technology also moved further. In fact, in one of the NPSM meeting when Jaravi was there, I was a member of that committee. I told her, why don't you make a shift of focus from microchips to MEMS and microchips for MEMS and borrow loans from the market and provide, in fact, you can invade the market in this region. But there was a mindset person, this did not happen. After that, maybe a very long time after that, NPSM gave some money, 50 crore, and something happened. But still, let me tell you, we are far, far, far behind the picture. This gives a comparable account of that silicon, stainless steel, and other semiconductor. You can have a look to stainless steel and silicon color. You'll find in many ways silicon has a better property, better mechanical properties. Hardness point of view, from Young's modulus point of view, lighter, much lighter than stainless steel, but other properties are very good. Similarly, quartz is very good. And people, there is a focus of interest from silicon, stainless steel was a unique process material for mechanical engineers to these things. Technology, I said that more or less similar technology is used. Some of the techniques which are used in microelectronics, same thing is also used in MEMS fabrication. For example, photolithography, anisotropic etching, chemical etching, reactive ion etching, reactive ion beam etching. These are techniques which are common to both MEMS and microelectronics. The other things are also used. And specifically for MEMS, there are certain techniques which are very specific to MEMS. Double-sided alignment and lithography, etch-stop processes, deep reactive ion, DRI, very popular, deep reactive ion etching. Also, Das process will give you some kind of details of that. Sacrificial layer etching for surface micromachining. Wafer bonding, very important issue for MEMS. Deposition of very special films which are not used normally in microfabrication, microelectronics. Liga process, not much in use today, but it was very important up to say about 15-20 years ago. Micromolding, as NIL, MCP, we shall discuss a little bit about that. And special packaging. MEMS packaging is entirely different from microelectronics packaging. It is the most critical issue in MEMS, the packaging, rather than the other manufacturing steps. Professor Nayak will tell about it. The micromachining, as I told you, is a starting process. It is nothing but the incorporate photolithography and etching. Let me tell you, same technique which is used in microfabrication in MEMS, in microelectronics, photolithography, and etching, they are modified or adapted suitable for producing microstructures in bulk or surface. If you do bulk microstructure, this is called bulk micromachining. And if you do structures on the surface, it's called surface micromachining. It is more or less, you understand that. Let me give you some important things which I think Dr. Das will give you detail. But basically, this is a very popular kind of diagram taken from books as well as from internet. I mentioned in the very beginning of both the presentations that my slides, some of the slides were prepared by me, but mostly were taken from internet and some from other sources like journals and books. This shows the bulk machining steps, 100 silicon wafer with a P plus diffusion in somewhere here. Then it is deposited, on which silicon nitride is deposited everywhere, and windows are opened in certain regions by photolithography. This is silicon nitride. Windows opened here, here, and here in a typical example. Then silicon nitride from this region, you make a anisotropic chemical etching. A chemical etching which reacts differently on different crystalline directions. In this particular example, say maybe etching in potassium hydroxide solution will have a very slow etch rate on 111 wall direction, whereas high, more or less rapid etching on 100 direction. As a result, these side walls are automatically created with 111 planes. And you note carefully that here I have made a V groove. By this, it is automatically self-terminating reaction. Two 111 planes have contacted here. No further reaction will take place. A V groove is created. In this case, a small nozzle is created, which is very common in our printer, DeskJet printer. In DeskJet printer, nozzles are created by this technology. Whereas here, you see that a membrane has been created because highly boron deposited region does not etch in the KOH solution. Automatically, there will be self-etch top. And this region, after the removal of the nitride, you get a membrane. And this membrane is very important in many applications in MEMS. Wait, anisotropic etching, I think Professor Das will give you some more details about this. Let us go into the surface micromachining. This is, of course, today is very important because MEMS structures are becoming very, very small and their bulk structures are not suitable. A typical example of surface micromachining. You take the substrate, deposit a layer, this layer is known as sacrificial layer for reasons which will be clear now. And you using a photolithography step, make a window, small opening here. And this is called anchor region. Repeat, I am repeating. Take a substrate which is silicon substrate, deposit a layer which is called, I will give you what are the layers, some details I will give you later. Deposit a layer which is called sacrificial layer all through. Then by photolithography make an opening here, and this region is called anchor region. Then next step, you deposit another film which is called structural layer, which is deposited in such a way that there is a conformal deposition everywhere. Okay, and you have made a photolithography step in this after this deposition, so that you get a structure like this. So I repeat. Next is structural layer deposition covering the anchor region, and the lithography and etching step to make a structure like this. Finally, do a step called sacrificial etching. You select a chemical which selectively reacts with the white region, which is called sacrificial layer, but does not react either with the surface substrate or with the structural layer. what happens? The etchant removes the sacrificial region even under the structural regions, and you get a cantilever suspended over the surface, anchored here. So this is a cantilever of another material anchored over silicon at this point and has multiple applications. In fact, there are 99% applications of MEMS today is cantilever based. Let me mention a few about some of the sacrificial layers, etc. And maybe Professor Das will discuss in detail about that. You can have a look. I'm not going into the details. Which one is suitable for sacrificial layer? Which one is suitable for microstructure? What is buffered kind of things? Okay? There are many problems in structural in surface micromachining. Main problem is sticking. Called what do you call it? Stiction. Some of you are doing research in this field. Stiction is a very important problem. It has to be avoided. The structure collapses and gets stuck to the surface. Unless you do special measures, the stiction cannot be avoided. And this is something has to be done for that. Molecular forces are involved, and mechanically, as an electromechanically, you have to do something. And one good advantage of surface micromachining is because everything is done from the top, just like microelectronics fabrication, you don't have to do anything from the back. So it is compatible with the microelectronics technology. And today's microchips, today's MEMS product, one thing must be mentioned here. MEMS, what is the full name for MEMS? Micro electromechanical systems, not sensors or actuators. System is complete with electronics. So you have to, if you are making a sensor along with the electronic circuitry has to be developed on the same chip. That is the ultimate target. But it is difficult to make the sensor and the chip on the same chip, the circuit on the same chip is a challenging task called integrated sensors or smart sensors. Okay, and bulk micromachining is not suitable for that because both sides are used. However, surface micromachining, which could be miniaturized to even nanoscale region today, okay, is compatible with the microelectronics fabrication and in certain cases in the today's advanced CMOS processing called CMOS compatible. This is very important, and which therefore slowly and steadily bulk micromachining is giving way to surface micromachining for advanced applications, not for ordinary applications. Deep reactive ion etching, I have told about it. A typical structure which is created by deep reacting will look like this. You have seen that how beautiful structure, the vertical is so, it is called, the width is smaller than the height. It is very difficult to achieve such structure in normal etching. Isn't it? Almost 100% vertical sidewalls and with a very narrow width, which is possible only by such process as deep reactive ion etching. And today's advanced MEMS technology uses that, and we are in India, we have sent several, including HCL, we have DRI. We are fortunate to have it. Another thing, as I told you, that bonding is a very important. In many cases, several silicon substrates or silicon and glass, etc., has to be bonded together. You cannot use an ordinary adhesive to bond it, then it is not strong. Sometimes there are very advanced epoxies nowadays available, but for many applications, just by epoxy bonding, you cannot do it. So there are techniques which originate from metallurgical processing. This can example of called glass to silicon anodic bonding, silicon to silicon bonding, silicon to glass bonding, etc. And these are very established techniques specific to MEMS technology. And at the end, in fact, I have to slowly because again time is coming up. But the next lecture is there. You see that MEMS can be classified in various ways, but in one typical way is that it could be a mechanical kind of MEMS, strain, pressure, flow rates, inertial parameters, etc. Thermal kind of MEMS, broadband, narrowband, IR detection, bolometer arrays, etc. Chemical, pH, gas sensors, electrochemical. Biological, medical, very, very important. Professor Das is in this group is doing very good work on this. Cell-specific, molecular-specific, implantable, non-implantable. These are some of the typical terminologies involved. Magnetic, yes, but very limited applications. Magnetic, Hall effect, magnetoresistive sensing. And one field, though I belong to the same department, I did not start that in my lab because of that reason. I do not know what is the reason behind it. I thought MEMS means mechanical kind of thing. MEMS could be my topic also, electronics topic. And that RF MEMS concept, which is so important today. Fortunately, I am involved in such projects today in some other groups, including here. And in fact, you can make many products by using MEMS technology for wireless applications. And switch, for example, and other things, sensor, various things. MEMS activities in IIT Kharagpur, Professor Das will tell about it. I was personally involved in some silicon MEMS development when I was here in the initial phase, where Professor Das and others was closely involved with me. Quartz MEMS along with ISRO. In fact, another lab of ISRO, we are fortunate that one lab is now in Trivandrum of Mr. Amitabh Bose. He utilized our facility for making quartz MEMS for acceleration sensing called double ending tuning fork, DTF. And the labs which you have seen in the earlier diagram, earlier picture, they are microelectronics lab, started during 80s and 90s in our lab, which has been further modified over the last 5-6 years. You can see a different new machines, new equipment, etc. But whatever I have shown is valid till 2003, 4, 5, did that particular era. But during the same time, NPSM was very effective, National Program for Smart Materials, was very effective, very active to set up certain labs. One lab we got in IIT Kharagpur along with IISc Bangalore, the MEMS design lab. In fact, the two labs initially started in India, one in IISc, then IIT Kharagpur, designed for designing MEMS structures. Afterward, there are many such labs were created, and this shows a picture of our MEMS lab where you will work. I will show you some structures which was created in IIT Kharagpur. In fact, IIT Kharagpur spent long time on development of accelerometers. Here I show a structure. Of course, it is simulated level, but we developed several such accelerometers in the lab in silicon. This. Achha, eta ki Foreman, will you discuss this in detail? Anyway, just let me tell you a little bit about this because I have another few minutes. This is a silicon microstructured here. This is called frame. Silicon is microstructured by photolithography and called micro machine in a structure like this, where this is a frame, rigid frame, and this is a suspended mass. We call it scoop mass, and which are suspended from the frame via 4 flexors, 4 beams, thin beams. It is freely, more or less suspended like this. Okay? And over these beams we deposit some resistors, deposit or grow some resistors, and which are shown in the next diagram. Resistors both at the frame end and at the mass end. So there are 8 resistors, 2 here at the frame ends, 2 here in the frame end, and 2 here at the mass end, 2 here. So 4 resistors which are near the frame and 4 resistors near the mass, tooth mass. Why they are there? Because from this analysis of stress or strain, it can be shown that at the where the beam starts at the frame end and at the mass end, the stiffness is maximum, the strain is maximum. So what will happen if you just deposit a device which can sense the strain, and in one side, then you cannot make it at the center, only at the 2 ends. And 2 ends, the nature of strain, you can see the diagram is just the opposite. You just see here the nature of the strain is like this. In this other side, it can be easily visualized. If you bend it like this, there is an expansion in the top and constriction in the middle. Like this, just the opposite. Same thing happens here. When you suspend this, then here there will be some little bit expansion and there will be little bit compression. And as a result, if you have 8 resistors made and they are configured in a bridge, Wheatstone bridge, in such a way that there is some cancellation, that when it is not subjected to anything, all the resistors are equal. When there is no pressure or nothing is there, all the resistors are equal, and Wheatstone bridge is configured in such a way, bridge is balanced out. But, sorry, I have another 2 minutes only. But if you now accelerate the device, that means if you mount it on the frame is mounted on a vehicle which is accelerated, getting accelerated, then the idler, the tooth mass will try to sit idle because of the inertia. So there will be it will look like this. So there will be strain developed on the beams, and as a result, the Wheatstone bridge will be disbalanced. The null position which was created earlier will be totally deviated. You can get an output now which is more or less proportional to the acceleration. It can be shown. That was the basic thing. On this particular principle, we developed various MEMS accelerometer structures in the lab, and we modified it. Ultimately, one factor is very important, that is the sensitivity. The other is called off-axis sensitivity or off-axis direction. And we worked out on it, and we developed some products for the National Development Program. And I think about 2-3 years back, a student also, Ravi Shankar, worked on it, and it was going on. Let us not go into the detail of that. We have all facilities for simulation here as well as fabrication. I will show you some very interesting things. We have also worked on quad, mentioned about quad microstructure. These are typical double-ended tuning fork we developed for. These also has acceleration sensor. We developed for, it is called IISU, ISRO Inertial Systems Unit. And it worked and it gave good name for us in the initially. And did electro fabrication, so Das did it fully. In fact, he was my student, PhD student. He did fantastic work, development work on this. So we are not going into the details. Maybe Showman will give you some time. Here, before that, for defense, we developed a dual tuning fork gyro chip, again made from silicon, from quartz. But this work is half complete because of lack of interest on the other side. We did not have the facility for testing. But we made the structure. I can show you some structure. This is the typical actual microphotograph of double-ended tuning for developed in the lab for defense. So I do not wish to drag on because this is a huge. This one, another picture. Let me tell you, this is something developed in the lab, in our lab, called thermal detector. This is based on thermopile principle. If you have a number of thermocouples connected in series, sensitivity increases. In the thermocouples, hot end is located on the membrane and cold ends are located on the remaining area. A small infrared energy falling on the membrane region increases the temperature rapidly because of the extremely small thermal mass. We developed this in the lab using polysilicon aluminum thermopile structure under an MTech project. So many other things are there. Let me stop here, I think. Let me conclude. So we have quickly glanced through the mother of MEMS and various other subsequent technologies which came up after microelectronics. The mother being microelectronics. I have given 50% time in that. How we have seen how the typical microstructures in electronics, they tended toward the nanostructures. This is a huge development. It is a huge dynamic development. And second is MEMS. MEMS, let me tell you, today MEMS structures are also going nano. That is the high-end MEMS. And you have heard of AFM, atomic force microscope. Do you know how it is detected? By a cantilever. So cantilever, you do not know how many. There are hundreds of applications in bio area where cantilever is used. It's a fantastic small thing, which is otherwise cantilever is cantilever mechanically. Bridge, big cantilever, Howrah Bridge. That is a different issue. But in a bigger dimension, universe, one side in the universe, explore the outside solar system, huge thing. The other side is go to smaller and smaller. Nuclear things were done earlier, but intermediately, outside nuclear, smaller things, that happened during last 10, 20, 15 years in the nano area. So our electronics is going towards nano and including MEMS also. Thank you very much for your attention. Thank you.
Thank you, sir, for the wonderful, informative introductory talk on our workshop. Now I would like to ask Professor Somen Das to kindly hand over a small moment to sir. Thank you, sir. Now there is a small change in the schedule. We have our next talk by Professor M.M. Nayak on packaging of MEMS devices.
Need it.
Right, yes. Oh, okay.
This side.
Okay, sir. Okay.
again, good morning. So, respected Professor Lahiri have made my life very simple now, because complete background, the history of microelectronics, MEMS, and also how informative and how educative it is. I think you understood as a student. Even I also became a student, I heard, and it was very systematically explained. And I think you know how the evolution taken place from a silicon in 1950s and earlier, even today, what happened. He has given the complete history as on today. So that makes my whatever I am going to talk will be very simple. And also the packaging, as he has explained, the anodic bonding, the eutectic bonding, and the fusion bonding and adhesion bonding, which I need not cover because he has given in a glimpse all the four and what is the temperatures it covers and all. So I can save some time in that also, and very systematic, because his experience and my experience, a lot of difference. I am basically a scientist and became a professor only 1 year, 1.5 years back. So how he actually teaches, I am very happy to see. First time, even though I had contact with him, I heard a lot of technical talks, but as a teacher, how he teaches, really fantastic. So thank you, sir. So I will be covering the MEMS packaging, but now the packaging word people may not like. That's why the Americans coined it as an integration. As on today, they call it as a system integration. So I put both. So system integration and MEMS packaging and overview. I'll be taking most of the examples and also showing you some of the animations so that you'll understand how the packaging is done of these, let it be a cantilever or a diaphragm or a hanging structure, how it is connected. Just I'll be going to show you to measure the resistance or measure its capacitance or impedance, whatever it may be, how you external world you connect, that's the thing. And but before that, we should know what is packaging. So you see the nature. We learn from the nature, mimicking the nature. See a bird, how the bird is packaged, how is feathers, and how is the bee, and how is the total structure as a bird. Just imagine a fish in water, how it is packaged. Always it has survived in the water. This is in all the atmospheric harsh conditions. A polar bear or some animal, how is the package? You see a human being, a child, for that matter a tree, and a tender coconut. If you really look into it, it's really a wonder. And you see here a human being, if you see the nervous system, the bone structure, the overall body, how? Total package. Just imagine if instead of eyes are here, if the back side, what happens? If head here, if in the leg, there's a head and legs are on your head. What happens? If you interchange some of the organs and see how it may look like. And even is the science fiction, you can even write a science fiction on that. So I don't want to explain because most of you know packaging means what and why it is required. But specifically for me to explain you the packaging part of it, I am going to give you some introduction on packaging and 3 levels of packaging. Normally it is 3 levels of packaging, and for aerospace packaging we are going for 4 levels. That also I will be good, just showing you the process flow, a brief process flow, materials for packaging. During the course of my talk, I will be covering the materials for packaging, what are the materials used, infrastructure required like wire bonding, anodic bonding has explained, and eutectic bonding and all, the wire bonding, die attach and all, what are the equipment, and maybe some animation on that. And 3D packaging at present, because you are very young, you will be not seeing the 2D packaging. Definitely will be going for seeing the 3D packaging. So something on 3D packaging and what are the types of 3D packaging. One case study, within the stipulated time, I have to give you one case study on transducers, packaging requirement for various types. It's not only one type, but how to have the requirement for various types, and briefly the summary. That's what I thought I will cover. Now what is packaging? So far it is called electronic packaging. What is electronic packaging? Because if you say MEMS packaging, it will be a little confusing. So I thought it's electronic packaging. At the heart of every electronic application, you take your mobile phone for example, you take this laptop, you take this a remote some device, you take anything, you take this projector, you take camera, how the packaging is done. So this is invisible but indispensable. So heart of every electron application you have this, is almost invisible but indispensable. You see that. Let it be biomedical device, a catheter tip camera. I'll be showing you that. Everything is, you cannot see, but it's invisible, but indispensable. What is packaging? Assembly plus integration technology. That becomes simply the packaging. You assemble everything, take the leads out, and interconnect to the external world. That becomes technology, integration technology, and it becomes the electronic packaging. Many people are not at all giving any value for this, undervalued by many, because we never give importance to our body. For example, if there's a pain in the leg, you know you have a leg. If you have stomach pain, then you know I have some problem in the stomach. If you have a headache, yes, I have a head. That's a headache. So this is undervalued by many, just for understanding's sake. But what is it and why? Why it is required? For example, I am holding this. If I simply I can use a PCB and click, this happens. But if I hold a PCB, a bare PCB with the components on that, what happens? There will be a short circuit, you may get a shock also, or there will be humidity problem. All this, you know, even if I drop it may. Your mobile phone, how many times you dropped? Nothing happened to the mobile phone, isn't it? Even in rain, heavy rain, you'll be riding your bike or something, it is completely wet, but still it works. So what is that makes it to work? If it's a bare PCB, whether it works? So it connects individual components. The first thing is it connects individual components. Let be a cantilever, let be a diaphragm, or that piezoresistors or some capacitor plates. It interconnects and it individual components. Protects the component device from, this is very important, protects the component and device from damage due to handling. I am handling this, your mobile you are handling, everything, camera you are handling, everything you are handling, even a laptop you are handling. It is damage due to handling. You know how the keyboard, somebody will press like that, somebody will very smoothly operate with, somebody will get sound. You know that, even then it has to, that is a harsh environment like. So you have to, so the damage due to handling, vibration. You may be going in a bike or car or cycle or something, or carrying your jumping or something, nothing should happen. Human. Same thing for even vehicles like a launch vehicle or a satellite or something, the vibration is very important factor. Shock, sudden drop, for example, suddenly a bump in a road, shock happens, but your system, your mobile is in your pocket or it may be in your bag or something. So moisture, very important. It may be heavily raining or it's a moist condition, AC or non-AC. Reliably dissipate heat. Everything heats up because it's having a battery or supply, it heats up. So how reliably you dissipate? Everything is covered under this packaging. So what is packaging? That is protects the components from all this damage, vibration, shock, moisture, and to dissipate heat. That's why the packaging very, very important for all this. Now I will give one example. This is one famous company, Fraunhofer at Germany. Even integrates electrons into a golf ball. Can you tell me why a golf ball one has to integrate the electronics, golf ball, and how harsh environment the golf ball and what the golf ball does? Can anybody tell me? For example, he hits that stick, a shock, you know, then nothing should happen to that. There may be a camera, there may be audio, sound recording by audio. It is having a sensor for range finding, or it is also sensor for angle, and also the altimeter, pressure sensor, all that, humidity sensor, everything. Now, why they have integrated electrons in a golf ball, when it hits, it should know what is the force, the shock it is imparting from the bat to the ball. Then it takes angle. What is the angle it moves? Is it 45 degrees, 30 degrees? What is the distance? It go on taking the photograph also and measure the distance, measure the height, takes the terrain photography, speed, the accelerometer, acceleration, everything. Even it knows where the detection of where it is going to, and it takes the coordinates of that. That means like your GPS can give with respect to time. So when you can integrate a golf ball, just think what are the requirements to integrate the electronics and MEMS device in a golf ball. So well-packaged electron devices continue to function reliably even in the harshest condition. The ball is going to be dropped, nothing should happen to that. It might have fallen from 100 feet, 200 feet. So modern packaging technology make developing smaller and smaller products possible. If I drop a big item from a height, some 100 or 10 feet or 20 feet, it may break. A small MEMS device, 1 mm by 1 mm or 2 mm, a small device, if I drop, nothing happens to that. You'll be seeing that why. And Professor Lahiri also explained you that scaling, but you're not able to go deep into that, but due to scaling, what advantage we get due to that. Then you have this the ICs or this particular Fraunhofer processor IC is thinner than the sheet of paper. In your ATM card or your credit card, you are not seeing any IC or something. No battery there, but still it operates. How it operates? Your ATM card or credit card, some magnetic strip. So no battery is required. Only magnetic strip is there or something else is there inside? In your smart identity card or something like that, something else is there? Any IC is there inside or something? Anybody can tell? Is it only magnetic card or something else? No. Something else is there. So this particular company makes it as thin as paper or thinner than the paper, so that for security purposes, if you give a document, I will know, yes, it is read by Professor Somandas, and how many pages he read, and what he read, and where it was, everything you can find out. That's how the latest technology, because Professor Lahiri explained to you that where we are going in the MEMS. So example, you have day-to-day example. You see, for electronic communication, hearing aid can fit discreetly and invisibly in the ear. You have seen about 10 years back, how was the hearing aid? How it was? Big one. Then what it happened? Just here only you will fix at the periphery, a small strip. Now you have one thing which is just put inside like a cotton bud or something like that. Now you cannot even see. So the technology, how it is evolved and how you get now, presently you cannot see whether he is really wearing the hearing, and including a battery you can put inside here. You cannot see. So he's a normal man. He's not having hearing aid, but he can listen. So if you have an acoustic microphone, or there may be a speaker, whatever it may be, is embedded with the battery, with the amplifier, with everything, whatever required. So that is one thing which is commercially is now going. It is worldwide. It is available. Automotive packaging. Without seeing you, I will be showing you one or two sensors on automotive packaging. You may think the automobile is simply a robust thing, but how much vibration? What is even in the Kashmir, Kargil, or in very hot places, it has survived. So temperature condition, vibration condition, accident means shock conditions, everything there. So that automotive packaging. One example I am just giving you. Electronic component system can be shaped to suit any applications. It can suit any application. You want in this shape? Yes. You want in this laptop? Yes. Your laptop you want in some other? Yes. Everything you can shape it depending upon your requirement. That's what. Anyhow, there are a lot of things which you can imagine to have this. So the more a product electronics become indistinguishable from the product itself, so the more important sealing and durability become. Means, for example, you see this, how it is packaged, light, but everything is a small wire and all. I can package this in a big way also, but not required. You want a sleek thing, so foldable sometimes, put it in the pocket and go. Even helmet nowadays, foldable is available. They call it as a MEMS helmet. Now some research is going on that. Just I'm telling you, to make your life simple. So single mobile phone, in the olden days, mobile phone is only for phone. Now what are the mobile phone, what are the things you can do? Is the mobile phone, or SMS you forget, and photograph you forget. Other than that, what are things? GPS and other things. Yes. So many, isn't it? Everything is there in that now. So much software and so much hardware and other things. How it happened. So everything is possible. So how you miniaturize things. So Moore's law and other things, know that. Some more examples. Now, if I have this thing and he is having a problem in the stomach, I cannot insert this. So you should have a catheter having a camera which is a small tip like a matchstick, smaller than that. So you can have a camera less than the matchstick size, the head of the matchstick size. That is possible. So for medicine, the world's smallest micro camera for endoscopy, and it is 1 by 1 by 1 mm cube. Only 1 millimeter, 1 millimeter. You cannot see that. Smaller than that. And that is how it goes inside the catheter. You can take an intestine or your stomach or anywhere. And even you have a stent or heart surgery, they use this type of. So the packaging is called the matchstick tip sensor packaging. That's what is gone inside. Just to give you the latest technology, which is actually again developed by Fraunhofer. And then lighting the high brightness LEDs. You have seen many of the vehicles, the high-end vehicles, in their headlamp. You see the LEDs now. I think many of you have seen. Why LEDs? Why LEDs? One is power. Then what are things? Brightness. Then yes, all things is possible by this. How LEDs are formed, I don't want to go deep into the process of that. Automotive packaging for a position sensor used for ABS, ASPS. Anything in the automobile, first it goes to automotive because a mass production and low cost, and then it goes to that. Then comes the power. We have to reduce the power. So testing and qualification of thick wire bonds in power electronics. Yes, we use the packaging, how technology different. Industry. For example, you have a rotating machinery. I want to know the pressure inside, the strain induced, the stress, the temperature, everything. But it's a rotating machinery. How you can get it? Everything is embedded in a, for example, there is a shaft and you have a vanes, blades, and you want to measure the strain, speed you want to measure, the pressure developed or cavitation you want to measure the temperature, anything you strain on each and every blades, and everything you want to measure at that. How you get out? You can't use the wires. Wire will twist, no? So you say RF or something, optical or RF like that. But your sensor should be so small, it should not induce some stress due to sensor itself. So everything is embedded in the shaft seal and how the sealing should be done and all those things, and it works on high temperatures like 400, 500, 600 centigrade. Your sensor should withstand, the actuator should withstand, the electron should withstand. So how you package it? So shaft seal with integrated energy sufficient sensors, and see, energy sufficient sensors for intelligence machinery. You cannot supply the energy from outside. You should have the battery or whatever power, RF power should be inside. Then security, integrating the ultra thin chips in the security documents. How you know that your document is not gone from here to Pakistan or some country? So can you embed these things inside? Can you do that? Yes, that is what is that. Now, if your laptop, if you are using, definitely even in America and US, they know that who is using, what is your password, everything is how it is through the wired system. But can you have a system, the security system, which you can use for defense purpose? So that is what security, not necessarily defense for any purpose. So these are the things. I am just giving an example. So any system you want to package, when you talk of microelectronics, or let me give an example of microelectronics, and MEMS you want to integrate, or you may have photonics or RF wireless, you want to integrate together, everything together. So we call this the microsystem technology together, microelectronics, MEMS, photonics, wireless, everything, microsystem technologies. Then it becomes a device packaging and the system packaging together becomes. So, but still, how to interconnect this is important. I will be showing you some of the slides on this. Now, the totally when you integrate, because MEMS, as Professor rightly pointed out, it is not only sensors, it is not only actuators, not only electronics, total packaging, total structure all together. MEMS, the MEMS as a sensor, as an actuator, as electronics, microelectronics, whatever is being built, and the structure, total structure that becomes. So that together it becomes a system engineering. So that is what is the total packaging for MEMS with the electronics. Now, one example I want to give you, the 3 levels of packaging. So you have 3 levels. One is called die level, a device level, or a system level. What it means? You have a die, small die. For example, you have a we call a silicon chip. After making some hundreds of things on a 4-inch wafer or 2-inch wafer, you dice it, cut it, and have a single chip. If you have that single chip, on that you have only the sensing element, it becomes only sensing element die. Now you want to put on that, as the professor rightly mentioned, an actuating link with some signal mapping or something, and it is a single die having a sensing element, maybe a cantilever, maybe to convert the piezoresistor into Wheatstone bridge and the electrical output, an amplifier, and an actuating element, maybe switch on and off or something like that. So all together in a single die, that is called level 1. That is the die level package. Everything on die level. It is interconnected through the aluminum metallization, thin film deposition, or gold, whatever it may be. But it is a single die. Everything it contains. That is called die level, level 1. Now you want to connect that one with the signal conditioning. You want to amplify it for 5 volts, 10 volts, some other things, or you want to convert to ADC, analog to digital converter, or you want digital to analog converter, anything. You have one more die. You connect this die with this die physically with the wires, maybe gold wires of 25 mil or something like that. That becomes device packaging level 2. Then you want a substrate, on that you put this one, paste it there, or with the adhesive you bond it. One more you have, you interconnect it, that becomes your level 2. Now it is not sufficient. You have to connect some power supply to that. So you have a power supply, you connect outside, some input action has to happen, some output, it has to give some output. You connect a digital voltmeter or an oscilloscope or something, multimeter for example, you connect it, and all this input action, everything what has pressure or acceleration or some physical phenomena which goes inside, together this becomes the system level packaging 3. That's what normally these are the 3 levels of microsystems packaging followed in MEMS. Just to give an example, one is the die level, one is the device level, and then finally the system level. That is the total is the system level. That's what is the thing. Now we'll just see for a space application, just because it's just continuing of one step further. We are continuing from the hierarchy of packaging for aerospace system. Why aerospace? I'm going. Even today, whatever you see, why it is rugged? Why these technologies become miniaturized? First, either defense or space they think, because we want to save the cost of a fuel or the total rocket or launch vehicle system. If we reduce the size of a sensor or actuator or something, for every 1 kg we launch on a payload or a satellite, 1 ton, approximately 1 ton of the propellant we can save in the launch, 1 ton. Means so few crores of rupees we can save. So how to make it smaller, lighter, and total size is smaller and better specifications. So the system, the hierarchy, what is used for aerospace system packaging is like this. You have the level 0, we call it that, level 1 you have seen, level 0. Here level 0, if you see here level 0, it is the intra-device connections. I told you on a chip itself you interconnect, that becomes intra-device. Maybe aluminum pads you will use and interconnect you use all that. Then you have level 1. They see this level 0 is nothing but this level 0. See L0 you have put this is a level 0. Die level, this is totally die level. So you can see the level 0. So this is nothing but this is itself is a die, this is a die. So this is the level 0. Now you connect the dies together, that will become level 1. So intra package connections between this die you connect intra package. So it may be a single chip, but it is having so many functions, but you have to connect this chip with this chip, some other chip. So all this you connect it, then it becomes level 1 in this case. Then you have one more similar device here that you interconnect on a PCB or some other board, that becomes your level 2. That's what we call level 2 is intra board connection. This is the board, on the board you interconnect, this is intra board connections. Now between this board and one more board, maybe ADC board, power board or driver circuit or something like that, you interconnect, that becomes level 3, intra box connections. So this is the intra box connections. So this is the platform, and box to box you can have one more, level 4. So this is the system hierarchy of packaging for aerospace system. So you have a single chip, then that many chips are put in one package, then on a PCB or 2-3 PCBs put together, finally it goes to a satellite or a launch vehicle or any system. So this is what is followed. Very briefly I am telling you about this, but to make this, yes, it may take few months or maybe number of days. Now this again I am telling, wafer level packaging is very, nowadays it's not that you package in the board level and all. When you want to give a 3D packaging or something, you can do it everything wafer level. That's why all the mobiles become so small and so many functions are happening. So you go for the wafer level itself. So you do everything in wafer level and you stack the wafers. I'll be showing you some of the things how you do that. So you do the highest integration density is possible with this, and it is a heterogeneous. It's not that homogeneous something. Each is different, but you have one wafer, one more like that. Many wafers you can have, but wafer to wafer connect, you should have a through silicon via. You should have holes like PCB. You have a PTH, isn't it? Printed circuit board. You have the printed through hole. So you like that here, you can have a through silicon vias you can have in that. So all processing steps are carried out at wafer level after actual front end processes have been completed. So that means all process steps are carried out at wafer level after actual front end processes have been completed. That's one level. Then here lateral widths almost identical to the chip dimensions. I'll be showing one example. The lateral width almost identical to the chip dimensions. Professor Lahiri has explained you even the lateral dimension and vertical dimension, how it is very close at present and those things. Example is here. So wafer system, everything in between. So the active, let it be a transistor or diode or something, and passive components are also included in the wafer interlayers. It can be one is only active, one be passive, or passive and active together, everything put together, you have that. So higher integration densities are possible here, and that is mainly due to 3D integration using TSV, that is through silicon vias. Through vias only you can interconnect it, and then it's possible. Example I have given here. See, gold and tin, you have a bumped gallium arsenide wafer. Pitch is 55 micron and diameter is 35 micron and height is 35 micron. You see this? Diameter 35 horizontally, height is also 30 microns. Almost same only, lateral and this direction same only. That means it's possible to have, it's not necessary to, like a building, you build vertically like that, but you have more same distance you can use for the both horizontally and vertically. It's possible. So this is an example of bumped gallium arsenide wafer with the 55 micron pitch as well as diameter 35 micron, height is 30. So pitch between this and this may be 55 microns, diameter of this itself is 35 micron, height also 30 microns. That's what. This is only just to give an example of a passive. So this is one example, and the process is a standard process. So normally, depending upon requirement, the overall process same, but which you want, you can select the process. So you start with the design, because everything, when you want the lead to take out, you have to design the, it's not that you design your cantilever or diaphragm and put the pad somewhere. It's very difficult to characterize. So plan in advance where to put your pads, because you have to take out, or you have to probe with the DC station and see what is the output, what is the resistance change, what is the impedance change, or what is IV characteristics and all that. So can you design your chip beginning itself thinking that, okay, my pad should not be at the center, at the corner, so I can take leads easily. You'll be seeing that somehow things. So you have a design itself. So various assembly and connection technologies on a multi-functional board. You have a design, simulation, redistribution. Once you simulate, you think, no, I should not have a cantilever here. I should be like somewhere here, and my pad may be here like this. So you redistribute depending upon the depending upon the requirement. You redistribute. Integration of passives is very important, because you may not know now if you are using for RF MEMS and other things, high frequency, or some you are using for some high frequency or low frequency measurement. You may have the noise. Maybe there is a what capacitance you call it as? Inter-electrode capacitance. Then there is so much of way noise can come in any of RF device or some other things, because we are talking millivolts or small volts, less, maybe ranges of less than 3 volts. What are the other things? Inter-electrode, then most of the electronics. What are the other things? What may happen? Some scooter is running there, or some generator or a fan is running, so it will pick up. So interference, electromagnetic interference can be there. So how to avoid interference? Okay, so you design your passive such a way that yes, you can avoid all that, and you can have, depending upon requirement, you can have silicon vias. Then this thin chip embedding you can do it, bumping you can do, singulation. I'll be showing you some more things. So bumping you do, singulation you do, means make it separate, because you know that by dicing, embed, then chip interconnection you can make, chip to chip, what I shown you between chip to chip interconnection. Finally you have to assemble it, encapsulate it, because the assembly itself is not sufficient. The wires and are exposed, the gold wire or aluminum wires are exposed. So you have to put a potting compound on that so that it is not visible normally, because humidity problem, maybe when you apply pressure, it may disconnect from the, because you have about 7 to 8 grams force only on these gold wires. So you have that. Then you have a various maybe optional interconnections, and then you qualify and test it. See that whether it withstands your shock, your vibration, your testing environment or not. You see that, and finally you check for reliability. You are doing one piece beautifully works. You do one more piece is not working, isn't it? In the lab, what happens? You do, for example, thin film deposition. You will be doing a sputtering or something. Today you get 100, 200 ohms. Tomorrow you do the same process, same person, same. Can you get to 200 ohms? No, not necessarily. You are not getting. You will tell, you will blame for the machine or something like that. Why you are not getting? Can you have a repeatable? All that can be have repeatable. Today I am getting 100 ohms. Tomorrow is 100. Day after tomorrow, and somebody else also does. Can you parameters? All the parameters can you standardize and see that yes, the machine is okay, the operator is okay, my parameter is okay. Can I get it? So that is very, very important. So see that the reliability is important, so that the repeatability is there on that. then only the product integration takes place. If it is not reliable, no use. Today my laptop is working beautifully, tomorrow it is not showing this. Instead of design it may show some other things, instead of saying, or is ulta it shows. What is the use? So no stability and repeatability. So can you have that? So that is what you have to see before you package it, because packaging any MEMS device maybe 10 rupees, 20 rupees, 100 rupees you can make it, but the package costs 10 times or 20 times more. So 5% may be the basic device, 95% cost is for packaging. So you should be very careful to choose. You will be using gold wire, you will be using a header, glass to metal seals, I will be showing you maybe very expensive things. So can you decide at this moment, can you have to use that or not? So those things. So of course simulation and testing, anyhow you use whatever the software you have, combined stress testing, vibration, moisture, temperature, whatever you want, aging and other things. So test it. Thermo mechanical simulation you can do, even it's a TSV via. What happens to via as a temperature is the increases or decreases, like a door. In the winter how the door will be, and summer how is the door? Either it opens because it's so big and which is a bulk. So you will be seeing that. But a small device, what happens to temperature 200 degrees, 300 degrees when it goes, the wafer experience at 200 degrees, what happens to via diameter? Whether there will be open circuit because the gold wire or gold leads are going there, or it may be gold coated, it peels off at that temperature, low temperature, it may be minus 40, minus 60, what happens to that? It compresses, so it collapses, all that. Then you see all the thermomechanical simulation also you do it, and then only you, yes, it's going to withstand all that, then you can go for packaging. That means the code design is important. That means when you plan your device, plan how you are going to take the lead out. Can you have a test structures in that? You have a cantilever, no doubt. You have a piezo resistor on that. Can you have a piezo resistor also outside? This is cantilever is here, but can you have one more similar resistor on the your hard surface someplace? Can you see what is the resistance change due to temperature of this and this? Why it changes? Temperature coefficient of expansion you will see, and you see all the maybe vibration, shock, whatever the interference happens. Can you see that? So you do that co-design. That's what it is written here. Highly integrated. That's a system design. Highly integrated system design can no longer be carried out independently of technology, and technology development cannot take place without considering electrical behavior. The term co-design is used to design this synergetic approach to technology and design. So when you design anything like our body, how the head, the inside brain and eyes, ears and all designed, and how it is interconnected. Just think of that. Can you do that? That's what I want to just give you. That's why background I gave you that. Now use anything, modeling, simulation, analysis, all the things you use combined together for the innovative electrical measurement. Use anything. First you do this analysis, do the simulation, do the modeling, everything. Then you take. Then can you do some R&D and see that yes, you are going to eliminate or reduce the effect of electromagnetic interference, RF issues, all these effects, design that. So that is what the subsequent connection to the incorporated system is also integrated in the design. So you any design, if you see all the, you can see even the present ICs, if you open, you see all the pads outside, not at the center. So well designed. Intel, for example, you see any Intel core, Intel thing, you see how the pads are designed and all. Just think how they designed, why it is designed. Example, for wire bonding we use normally, it's called ball bonding. We also have wedge bonding, and for die bonding we use the reflow in air in some cases. All these are ultrasonic bonding techniques, thermosonic bonding techniques. You can see that it bonds the wire from one place to other place. You may have a pad at the outside here, it bonds there, a 1 mil wire for example. 1 mil is 25 micron wire, it bonds, a gold wire or aluminum wire, it bonds. Aluminum wire sometimes will be 33 microns bonds, and the strength of this should be around 7 to 8 grams normally. Some of the application we want 10 to 20 grams, and Professor Lahiri knows that, because for aerospace application we put not one bond, we may put 2 or 3 for redundancy. One breaks out. So what happens in a satellite if there is an open circuit? You will lose everything. In a vehicle when you go, if something a problem is there, yeah, somebody can come and repair it, but there is nobody to repair. So you do that. Now you see this reflow. This is one more ultrasonic wire bonding technique, where you bond automatically. Once you know the pitch and once you know the distance, you can, like a CNC, computer numerical control system, you can simply give the instructions. So it simply bonds between 2 pads or 3 pads, depending upon the requirement. You can do that. So then you have a wedge bonding. You want more strength for your bonding. You have a wedge bonding here. So that also we'll be seeing. Yes. So this is a wedge bonding. Where is more strength? You want to about 20 grams, 30 grams weight. When you pull also, nothing should come out. So you have this. This is, you have a wedge bonding technique. Just to give you an idea. So that, and I have a lot of YouTube things, but I don't want to show because it may take a lot of time for you to see that. And I think I don't know, you've seen the die bonding, how we bond the die. So the die is attached depending upon the requirement. It looks simple, putting an adhesive and if the temperature expansion of a PCB or wherever you are bonding is different than this, it simply in low temperature can come out. So temperature, that coefficient of expansion of this and this has to match. So you should choose a die such a way that it is also having the same temperature coefficient. If it is a glass, what is the coefficient of expansion? If it is a metal, what is that? If it is a PCB, FR4 PCB, what is it? You have to select the thing. One is the temperature. Second thing is it you want thermally conductive or thermally insulating you want? Or electrically conductive or electric? You want thermally conductive, electrically insulating. Yes, you have to use similar dies. There are some places you want thermally to have a good conductor between that. So these are the things what you have to see when you do the selection for your thing. Now, let us take MEMS devices. You may have different MEMS devices. Here, for example, you have the devices inside. So I have put some, for just to give an idea. You have a mechanical device, a cantilever, for example. How you operate from outside? Cantilever is fully packaged, but something has to act on that. Maybe you want to use for biological applications. Something sit on the atoms or your molecules or some biofluid has to sit on that. So you should have an opening for that. At the same time, you should not deteriorate the functioning of this thing. So how you make that? Say cantilever may be outside, it may be displacement sensing, or it may be vibration sensing, or maybe how you connect it that. Or you may have a chemical, just a gas sensing. Maybe CO2 you want to sense, or you want to see methane, or you want to see hydrogen sensing, or you want to see some your cooking gas sensing. So you want a window, but you have a mesh there, maybe a mesh like thing. So that chemical, how you package it. Then you may have a optoelectronic or optical, so this thing, optical window. You have a transparent window, and whether it is you want, which way you want to connect that optical window, how you package it, that's important. Then microfluidic, you want to see the flow, blood flow, for example, or you want to flow of some liquids, or you want to see the density of a liquid, or you want to see the viscosity of the liquid, or you want to see the level of the liquid, how you interconnect it. So it's a microfluidic channel. Maybe somebody is covering in the microfluidics, so I am not covering that, so fluidic channel. So you have to interconnect. Now the power you have to give. So how you get the maybe 5 volts, maybe 10 volts or 20 volts, whatever it may be, the power you have to input. And signal you have to get out. What is this? Is it, what is the lumens, or what is the optical property? So you have to get an output. Thermal, heating or cooling, you want to measure the temperature, how you connect it. So in electron, if you see the IC, it's only electrical things are happening inside. You're completely encapsulated, only leads are coming out in IC, any integrated circuit or any ASIC comes like that. Here is not like that. In MEMS you have some, for your physical phenomena to measure, to have an output, you should require some opening to the outside world. That's what I want to show. So for photonic you want to have a opening. So this is how the package you have to think in advance. That you are going for only fluidic, or you want only the optical, or you want only chemical sensing or gas sensing, or you want mechanical sensing or thermal, microfluidic, anything. Can I design my header or my package to suit these applications? That's one thing. Now, how to integrate? Yes, of course, you may have a IC, you may have a low noise amplifier, you have a driver amplifier, you may have a switch or mixer or preamplifier or anything. So how you interconnect this is important. It's the first part of thing with MEMS and other things, how you interconnect all this. It is not, I am showing you overall thing. It may not be for all the things. Some of the things only you may require. You may require a VCO, or you may require a driver amplifier or something like that. Now you may have a thin actives, you have a passives like a filters, antenna, a waveguide, MEMS device, anything you can have, like RF MEMS you can have. Cables and connectors, anything you take device, cable has to come. In this also cable will be there. They remove the interconnect. Even your mobile phone, when you want to connect photos, you have to download you want a phone, isn't it? So everywhere you require cables or connect. How you interconnect at which place? See, nicely they have put in your laptop, well designed aesthetically. Where USB port? Where is the power? Where is your this interconnection to the projectors? Everything is planned. If it is not planned, bottom side, bottom of the laptop, for example, you have this connectors. Or in the top, on the top surface, if it is there, how you do it? So how you are planning it? Just think. So can you have those interconnections properly put? So system packaging we are talking about. Boards, which type of boards you have to use? Whether it goes to high temperature, is it okay? Or in low temperature, can I use FR4 or some PCBs? Thermal structures, design. Is it a plastic is sufficient? Here, okay, it is only ambient, plastic is sufficient. When you go to high temperature, low temperature, can I have that? Then power sources. How we are going to connect the power sources? It may be a small battery here, a big battery or RF source, whatever it may be. So total thing, when you think and put it in drawing board, it becomes a system package. That is the IC integration, system integration. That's what is very, very important. So I'll be giving you also some references whoever are interested in that. But commonly used here, many places, most of you are hearing of, it will be SOP package or SIP, system in package, or SOC, system on chip, or SOB, system on board, or MCM, multi-chip module, TSV, through silicon. All this as an electronic or a MEMS, you will be listening to that. Many people will be knowing what is SOP, what is SIP, what is, but we should know because we will be using as a MEMS or ASIC or a IC, will be using all these packages in our day-to-day life. When you make any MEMS device workable and you want to produce a device and you want to repeat the, yes. So we have a SOP, system on package. We will be seeing that what is the system on package. Every system on the single package, how it will be done. System in package, what is the difference between a system on package and system in package? You will be seeing system on chip, everything on a single chip, that will be seeing. System on board, like I shown you previously, on a board you have a lot of systems, you will be seeing that. Multi-chip module, one module but you have multi-chip inside, you can have that. Then through silicon via, those things. So this is a through silicon via. These are the various packages, what I am going to explain you. May not be in very detail, but some of the things. So the current technology as on today, what normally, let it be Intel or let it be any IBM or something they use, the current system is a SOC, system on chip, everything on a chip. So based on the complete system on one chip, so everything can be on one chip. That will be your Intel core you talk or you talk anything, so what do you do? A complete system on a one chip. Then multi-chip module, based on the interconnected components. You want a IO port, or you want some serial interface, you want a parallel interface, or you want something RF interface. So can you have the multi-chip module? Then system in package, based on the stacked chip, stacking like a multi-story building. So stacked chip package. This is on like 3D package for reduce the form factor. Real estate is very expensive, you know. In Delhi or Calcutta, if you want to take 20 meter by 10 meters or 25, how costly it is. So like that here also cost will increase. So can you go vertically? So these are the things, what you see this. And one example I want to give you, because you have to see also know how these all systems are integrated in single chip. I want to give you one commercial chip, ZMD31050, advanced differential sensor signal conditioner for either pressure or some of the Wheatstone bridge configuration, whatever you do, how one can interface a ZMD chip and what it contains. I want to give you very briefly, I want to show you about this. So it is not for advertisement or publicity, just I thought to make you understand what are the things available in a single ZMD. There are similar, many chips are there, but I just thought a MEMS, when you interconnect, which chip normally a pressure sensor people they use. So CMOS integrated circuit for high amplification and sensor specific correction of bridge sensor signals. A bridge can be balanced or it is not balanced, offset is there. How to make it an automatically the zero balance or balance the bridge. How to compensate for temperature, how to compensate for excitation, how to compensate for the sensitivity, all that will be in that. So no external trimming components required. You need not put any resistor or any network outside. So how you can do it with the software technique, and it's called active compensation. So PC control configuration and calibration via digital interface. So how simple it is and how accuracy you can attain, different accuracies at different temperatures, those things. So basically, I'm not going to go deep into this chip, but just to give you an idea So you have a resistive bridge network, maybe a pressure or maybe accelerometer or something like that. So you have a programmable gain amplifier. So whatever gain you want only 5 volts, 4 volts, 3 volts, 2 volts, you can program that. You have multiplexer there, you can multiplex the temperature sensor with your pressure sensor readings. You have analog to digital converter, you have EPROMs, you have CMC, you have a ROM, you have a digital to analog converter, you have pulse width modulation, C compensation, you have a, what is that, a single serial interface, all the interface and everything you have. So everything is built in a single chip of maybe 5 mm by 6 mm or 6 mm by 7 mm by 7 mm, that's all totally. So it's possible to have this. That means you can do anything. You want to 5 volts output you want for 1 atmosphere you want or 10 atmosphere you want. How you connect the piezoresistive bridge to that and automatically compensate it for not only ambient conditions. I want Pakka 0. This bridge, whatever you do piezoresistors in processing, you may not get, say for example 1 kilo ohms you want each arm. Can you get in processing exactly 1 kilo ohm? You cannot get 1 kilo ohm. One may be 1.1, one may be 0.999 or something like that. It's not possible to get. That means when you excite the bridge, you may get some imbalance. So that offset you have to compensate it. Automatically you have to compensate. Number one. Due to temperature, when you increase the temperature, there is a possibility of change of the resistances or decrease of the resistance depending upon the temperature. Each resistor may vary differently. Each resistor. So can you compensate for that? Because you don't want output due to temperature, you want output due to the pressure only. So any other external harsh environment you have to avoid. I'll be showing you one slide on that. So can you do that? Yes, you can compensate for temperature because you measure, you have a temperature sensor, you measure the temperature, depending upon that you give some input, you can compensate for that. It's possible. So when you compensate, Professor Lahiri told you there is a strain gauge. When you apply stress, there is a change in resistance. Apply strain, there is a change in resistance. Now the resistance change is there in the ambient condition. Due to temperature, this element it may expand or contract. So what output you get is different. Can you compensate for that? So the temperature compensation due to zero offset, due to the sensitivity and due to the full scale, all things you can compensate using that. That means the gauge factor itself may change. For that all you can compensate using this one of the things. There is one more chip actually. What is that? Is MAX 1452 for Maxim 14. One can use that also. So this technology already explained to Professor. So we know from SSI, from GSI, the giga scale integration. We know over 100 million transistors, equivalent gates are now presently available for supercomputer. And you know the typical number of IOs are more than 10,000. All this I need not again repeat these things. But silicon via, what the technology at present, use the MEMS silicon fabrication process using the glass bonding technique by anodic bonding or any type of bonding. You have a silicon fabricated device which you have to package, sandwich between two silicon wafers, and how the vias is put in this. Those things I want to just show you. So this is the process. I think Professor Soman Das will explain on the silicon fabrication processes more on these details. So I don't want to go, but it is possible to have thousands of devices. You want hermetical sealing? Yes. You want some gas to be incorporated in this nitrogen gas or argon gas? Yes, it is possible. And you can have an optical hole you want, or you want to apply a pressure here, and you want to have a diaphragm? Yes. Or you want a gas sensor, you want a meshing here? That is possible. Anything. You want to have a cantilever? Yes. So anything is possible. How this silicon process, how you plan it for packaging is important. Now gyros, you know, again Professor has explained you about the how the gyros now for automotive, even your the latest Android or whatever your things, this gyro is incorporated. So you know it's what are the advantage of having this. This is one of the automotive gyro of sensor nodes own product on the cars. How this is one of the example. Of course, the RF MEMS, again the explanation is given, so I need not go in that. This is important, very interesting, and the smart dust. Once Professor TK or Bhattacharya also was talking about this, and it is an US, Berkeley and JPL, that is Jet Propulsion Labs, how they did initially the first smart dust, it is called, or modes. So the network, a wireless network to measure maybe outside, you want to measure the temperature, you want to measure the humidity, you want the soil moisture, you want the wind velocity, you want wind direction, you want vibration, everything it measures, and just you will get in your like mobile phone by wireless network. So it's a wireless network. Mainly at present they are using for all the automatic weather stations, and also now used for many of the nuclear plants and some of the hazardous places where you can use it. So these are the place where you want is a tiny device, and it should be kept anywhere, and it has to do all the jobs. Can you do that? Yes. Using the MEMS is very easy, and now they become very famous, and in many of the godowns and other things, many godowns where you store a lot of items, you don't know where you stored. Now itself in our house we don't know where I have stored our item. So can you just see and get, yes, my item is on the 4th floor, 3rd rack, 2nd drawer, first thing. So you will get all information because you have an ID tag, RFID tag or something like that. Can you get that? The storage of lakhs and lakhs of items in one godown, can you identify? Now this technique has gone not only for that, any fire happens or something disaster or a flood, water is entering inside, can you understand what is happening inside when you are not there, you are some far away. So all that now, this same technology is actually now gone to the deep into the things. So coming to the main thing is this system on package, very important. What is essential? See, you may have a mixed signal, you may have a digital only or RF or optoelectronic, MEMS and bio and nano nowadays. So embedded actives. Therefore, all this you have to think when you design your system on package. You plan, not just simply think, okay, I'll do this, and finally you think, oh, I done some mistake. Or can you think in beginning itself, is it a mixed signal or only digital or only RF or something? Based on that, can you decide the package what you want? Is a plastic package, a metal package you want, or what package you want? So these are some of the essential things what I wanted just to show you. But still, one should know the definition here. When you design the package, one should know what is the difference between multi-chip module and SIP. What is the SOC and SOB? What is the difference between that? We know that just it is a MCM is multi-chip module. Okay, can I use a multi-chip module or SIP? There the doubt comes. Can you go for MCM or SOC? So how to define this? So this MCM is a package enabled integration. Package enabled integration. You see the wording, package enabled, and SIP also package enabled integration. But what is the difference between this and this? This is a 2D. So horizontal it is. Everything is horizontal. 2D. 2 or more chips interconnected on a single carrier. Single carrier, one chip, 2 chips. So anything you can interconnect. That is one. Together with the board, it forms a system. Whereas this is also package enabled, but 2 or more is stacked. What is the stacking? Go one above the other. So it's a stacking. So that is the difference. And requires system board. You have a system board and you stack it, not horizontal. That is the difference between MCM and SIP. But now what is SOC? IC integration. Highly integrated and mixed signal ICs. So this is highly integrated and mixed signal. Partial system functions is one component. See, this itself, SOC itself you can use as a single component. That's what we are going to. Then SOB, current approach to system assembly is this SOB, system on board. Discrete components assembled on a system board, a laptop, or you take your mobile phone. So normally they use this SOB technique because so many things are there. So each manufacturer is different. Maybe your sound system or mic or a speaker made by somebody, or acoustic sensor made by somebody, the basic chip is somebody, and IO somebody. So you integrate. Then SOP, best of package and chip integration. This is best of package and chip integration. So this is micro miniaturized single package system with 2 or more embedded RF and digital, analog, optical, everything put together. This is on the best package, chip integration. So these are the things what the basic definition of the MCM, SIP, SOC, SOB and SOP. So these are the things. The trends is not that we stop at SOC. What is the SOP? There is further, it is subdivided into the multi-technology, high performance, power efficient. So if you put SOC in MT, you want multi-technology, yes, MT. You want high performance, you put just HP. So depending upon that, you have to choose your package. It's not that just high performance means not just it is same header or same package. It's a little different. It is having higher cost and better temperature variation, better temperature withstanding capability, more strength and all that. Power efficient means yes, the dissipation is very good in that. So depending upon that, it is you have to select. So I'm not going deep into that because it goes deep into the packaging. So it will be a little bit boring subject if you go deep into only packaging. Now the challenges to be addressed when you design any MEMS and integration or something. So first you design, verify, test it, and manufacturability is possible or not. You can design anything. Recently we went to an NP mass project. One person designed 1 micron pillar, and for 2 mm, 1 micron silicon pillar or some pillar you want 2 mm or 3 mm. Is it possible physically to make 1 micron pillar at present technology to about 2 to 3 mm? Is it possible? Kundu, is it possible to do? Where? Silicon? No, pillar. It will be like that. But he made all the ANSI simulation, COMSOL simulation, everything, has given all the results. People are all nodding head. But I asked you one question: can you fabricate 1 micron pillar? So like fabricating your 1 mm, it has to stand vertically some 10 meters, 1 mm but 10 meters. Can any material at present possible? Even nanometals, CNT or graphene, very difficult. So it is very easy to design in any software and your tools, but you have to see that manufacturability. You see what facility is there in IIT Kharagpur, what facility is that at IIT Bombay or IIC. Is it possible to do so? Manufacturability. Yes, implemented. Yes. No, 1 millimeter. No. He is telling about 3, 4, 5 millimeters at present technology. Some, yes. Yes, it is possible. But I am telling he is going to fabricate in some fabs, he was telling, within 1 month or so. So that's what it is very difficult to do. Very difficult to do. So imagine what is manufacturing thing available and how to do that, those things. Then IP and legal. See, normally we copy it. Like what we do, we take one paper, based on that we do it. You copy it, no doubt. But why not you use your innovations, your thinking, change that some mindset. Don't only copy IEEE paper or some sensor and actuators, you copy and do it. No. So there will be IB and legal issues. Yield. When you say manufacturability, after doing you want 10, 25 numbers you do, but only one will working. Not good, no. At least 25, 20 should work, or 15 should work. Not all, only one is working out of 25 when you do devices. So you see the yield, how much it can yield from the whatever you designed, whether it gives a yield or not. Final. Then development time and cost. You have made beautiful design, but it takes 3 years to get it out, and cost is a few lakhs. Not interested. So you think all the challenges and well in advance. So how to package everything you see. So power management you have to see. You have to see reduce noise margins. Noise very important. You will be talking microvolts or millivolts or something, but noise is more than millivolt or microvolt. So how to avoid noise in the design itself? You can have that grounding, or you want earthing or grounding or guarding, or what is that? You have so many things, techniques to do that. So how to do that? Shielding, for example, crosstalk, increased crosstalk, comprehensive system level simulation and simulation of digital analog interface. This is important. You simply don't only see your cantilever and diaphragm or something and design. See everything together with the interface and everything. Then you can simulate and check is it okay or not. Mask and tooling costs. We always forget once I make, okay, my silicon is only 10 rupees and my over. But what is the cost of mask? Mask is very expensive. And what is the tooling cost? Making the mask and other tooling costs. Those things also take care of when you do it. Because you are all going to be, engineers, your PhDs you want to do, then you want to find out what is these things. Yield, increased number of metal layers and random defects in metallization. Always you have a problem when you have an increased number of metal layers, when you make via or something like that, you have the rejections are more there. So you have to see that how to reduce the defects and get good yield. Then some common test bench infrastructure. I don't want to wire it, but I want to see on the DC probe station or multimeter or oscilloscope. Can I connect it to my small probe? Probe is only 1 mm by 1 mm, but when I put my probe with the crocodile clip, all that metallization will simply goes away. So can I have some structure, can put a PCB and then connect it? All plan in advance, then it is possible to test your device and see that its performance. That's the one thing. Then see the presently is one of again taken from that Fraunhofer. If you see the biggest barrier business challenge. See, you are more than $10 million of investment. So it takes more than 18 months to design and ramp up to get it. 18 months it takes. So see, 10 millions and 18 months. So market size should be for this at least 60 to 100 million, even 10 million investment. The market size, if you know, that's why the mobile market is coming up. India is having, I think, next to China, highest mobile phones. Even a beggar is having a mobile phone. He talks, I am here, and a lot of people are there in Howrah railway station. Why not you also come beg? So he will come. So he comes. Yes, I have seen in some places they'll call their colleagues by mobile phone. He comes and comes. No, you see, even a servant maid or a carpenter or everybody is how useful is a milkman or something, isn't it? So it is the, it is, you may forget about a wife, but you never forget your mobile, isn't it? You know, so the mobile became a part and parcel of our body. So that's what I'm trying. So unless that type of market is there, that's why let be China or Japan or US, why they are jumping on India on the mobile market and how to make it. So not so many opportunities. So India is not doing that, but so just I'm telling about this. Now we'll go specifically for 3D packaging. What are the types of 3D packaging we have? Just it is better to see some of the 3D packaging challenges and 3D packaging, how it looks like at least. You may not use, you may use future. 1 or 2 people may go to such industries and use it. So what is the 3D packaging and what is that? I am giving an assortment of respected to 3D packaging approaches, some of the things. So you see these stacked packages. When it's simple PCBs, you see your old PC, you open it, you see, isn't it, motherboard, and you have inserted the your various boards. So yeah, cards. So that is the stacked packages, low density and low technology, old technology. Now you don't want that, no. You want, now how flat is your, previously how was your monitor? So big. I have seen many monitors in the same building is being discarded in the backside, big monitor. But now how is the monitor size? Huh? So sleek, so slim, so beautiful. So it is the, so now this is the old technology, stacked, but still it goes on the power devices. This is the stacked packages, low density and low technology, still required for some cases where the is not very important. Then wire bonded and die stacking. You see, you wire bonded, but stack the dies and wire bond to the other, whatever your interconnecting board is there. So you simply wire bond, maybe 1 mil or 33 mil wire, you wire gold wire or aluminum wire, or now presently copper wire bonding using that machines what I shown you, the bonding machines. You have the wire bonding and die stacking. So one more technology. Now you want it's not 2. I have 5, 6, 7. Yes, you can have a tower of Hanoi. Means you can have a bigger one here, lower one. You have to design, but think: can I have power here or power here? You have to have power supply board here because you have to dissipate more heat. Then your sensor module can be here. So how to interconnect? Design in advance so that you know how to interconnect all these 4, 5, 6 boards in this way, pyramid construction. So can you do it? This is a tower of Hanoi. So this is one thing. I have given you references also here in the bottom. You may not, in this reference MEMS packaging by Thairan Su. Given this, I am teaching to the PhD student of institute 1 full semester all this, but I am condensing everything in 1 hour, 1.5 hours. So staggered die. So you can have a die staggered way and interconnect it. This is also a technique of connecting the various boards or the wafers. This is one way of doing it. Then you have folded die, like a folded umbrella. Everybody wants less luggage, isn't it? So more economical and less luggage, more comfortable. So you can have this one. You can have folded thing like your fan, or to use it for this thing. So you have here the, you can fold like this, like this. You can even double fold also. You have nowadays. So folded die. This is also being used at present. Many applications, specifically for space application, where you have sold our solar cells, how it is actually opening, closing, and all that. So that is possible to do on the solar cell and other things. So there is a folded die is like that. So they can have, and you can have any type of and any number of dies interconnected with the folded die. This is one more technique. These are 3D packaging. This is a 3D, 3-dimensional packaging. Like you have underground parking. How your vehicle will be, on not your visibility goes underground and you can park it. Similarly, you can have all these mezzanine multi-chip modules. All things are parked one below the other like that. You can have this type of assembly. Depending upon your requirement, depending upon the density what you want. Yes, but power, you have to consider how the heat dissipation and other things. This is one more. This is the low profile pattern overlay. So you can have not necessarily wire bonding everywhere. You can have your pattern, the metallization itself can be like that. And like a motherboard, you have a connector. You can have similarly in this, it can be stacked like that. Only wherever you require, only those things can be interconnected either this way or both ways. It's possible to interconnect. So the low profile patterned overlay die, this is one more technique. Just giving you an idea what are the 3D packages available, like building a multi-story building. So how to do that? That's some of the techniques. Not that everything is available everywhere, but wherever is required, we should have. So then you have like a book. You have many pages in the book, and you have to interconnect them. Yes, that is what is the stacked pattern die frame. So you have like a book, and you want first and second, second and third and fifth, anything you can interconnect both sides, that side or this side. Normally on one sided. So it is not necessary that you have to everything you connect. Only these two maybe you want to connect, or so first and last. Power you want for everywhere, yeah, you connect here, all that. Don't want power only, you want only the signal, only wherever you want and amplify. So these are the things possible. The stacked patterned die frame. This is one more technique of. This is a monolithic wafer stack, where the TSV, that through silicon via use. So use the wafers and that you interconnect. That is the latest technology what people use for monolithic wafer stack. They use it and they connect it, interconnect, and you get a very high density and good efficiency and high reliability and low cost. That's what the latest. So of course, all these stacked pattern overlay MCM, everything looks like that. Is interconnected in different layers, and each layer is also depending upon the requirement. It's interconnected. You can see here how it is interconnected. This layer, and only these two layers how it is interconnected. You can see that. So all this is possible in 3D packaging approach. That's what. So I have explained you very briefly this type. All these are 1, 2, 3, 4, 5, 6, 7, 8, 9 types of 10 types of packaging, 3D packaging approaches. Assortment of these are different. Of course, the combination of these also possible. You combine this and this, combine this and this, combine this. That's also possible. But these are what are the basic things available, and this they normally use for high density packaging, high density packaging, and for low density packaging one can go for these things. Just to give an idea of 3 levels of packaging. Now one example I want to give you. So just to make you more understand on a specific things. A sensor. What is a sensor? Every one of you know what is a sensor? Or a transducer. One form. Can I call this converts electricity into light? Can I call it a transducer? Or fan converts electricity into mechanical? Can I call? What is the sensor? Huh? Measurement, yes. What you want is physically you want to measure something physical, some measure and input you give, and you want an output, electrical output. Why electrical output? Why electrical? Why not mechanical? Why not chemical? Yes, exactly. You can have an indication, you can have recording, you can have measurement accurate, you can have control. Like AC, it controls the temperature, it controls the, see it is nicely controlling this temperature to say 24 degrees. It measures the temperature, gives the indication to the compressor, so switch on the compressor to make it still cooler or not, and switch off if it's overcooled, or switch on the heater depending on the requirement. So you have a sensor, you have actuator and everything. So the sensor mainly used for this purpose, and some of things requires excitation or no. You know the passive and active. I am not going to that sensors. No, I am not talking about a simple sensor, but the sensor should withstand all the harsh environment. Whenever you do, whatever you do, a sensor, not just a sensor. It will be in lab, it's okay. But sometimes these sensor, for example, we will take a pressure sensor, which has to measure the fuel or oxidizer or very acid or alkali or some natural gas and all. Your chip, silicon chip has to withstand all the acidic thing. You have that silicon is there and it may etch out. You have a metal on that, maybe aluminum or gold. Wires are there, come out. There is an epoxy which is bonded. Something comes. So can you how you isolate from this? So that is one thing. Second, output you are getting. When you get output, how you take it out is important. But that output may vary not only due to pressure, due to radiation. It may be solar radiation, gamma radiation, nuclear radiation. Due to radiation also there may be positive. Then acoustic, somebody is talking. It's a pressure sensor. What is our sound level? That also a pressure. So that also may vary. So can you, I don't want, I have to reject this acoustic noise, only I want to measure this pressure. How to do that? Temperature. Temperature increases, decreases, you don't know. Today temperature is 33 or 34 degrees at Kharagpur. But when I take the sensor to Kashmir, where it's 0 degree or minus some temperature, it has to behave the same way. But due to temperature, there may be expansion, contraction of the resistors, or something is happening, some other output should give. How to compensate for temperature? Vibration. Due to vibration, NAV is a piezoresistor, anything you vibrate, it will give an output. Due to vibration also I may get output. So how to eliminate that, which I don't want, is the interference. Mechanical shock, while it is simply hitting, anything may change output. How to do that? Impact, watt hammer effect, anything. Vacuum. I have used the sensor here, very beautiful works. I have put in a vacuum chamber, your maybe sputtering unit or vacuum evaporation or some vacuum chamber I have put. It is not functioning. You will tell it is not functioning. How to make it to function? And noise, EMI, EMC, everything. There will be pump is running, rotary pump, diffusion pump is running, turbomolecular pump is running, some pump is running, some machines are on, so many things are on. It gives some output. I don't want that. How to avoid that? Humidity, a humid atmosphere. Or it is there is a thermal shock. So many things. I want to use underwater. I want a deep space or planet. Smoke is there. Lightning is happening. Thunder, earthquake, solar wind. So many unwanted things are happening. Still it has to function. How to package it is important. So can you take care of all this? You eliminate all this. Only just how to package it is important. Just to give you an example of one sensor for space application, I want to give you. But the pressure, when you say pressure, measurement of pressure itself is important. What is the atmospheric pressure in Kharagpur? Somebody can tell me. What is the atmospheric pressure in Kharagpur? Huh? Approximately. Kharagpur atmospheric pressure. No. Approximately. Okay, what is the normal pressure in anywhere? Huh? 1 bar. What is 1 bar means what? How many millimeters of mercury? Okay, we are very close. 760 millimeters of mercury equal to 1 atmosphere. 760 equal to 1 atmosphere. 1 bar equal to 750. You should know precisely 750. 10 to the power 5 pascals. So even the 10 mm counts. 1 bar equal to 750 millimeters of mercury. 1 atmosphere 760 millimeters of mercury. Okay, so 1 bar equal to 10 to the power 5 pascals. 10 to the power 5 pascals. 1 followed by 5 zeros pascals. So now you have a vacuum, reference vacuum, thinking it is a pakka 0. With respect to that, I want to measure the pressure P1. Whatever you want to measure the P1 with respect to atmosphere, now a vacuum, we call it absolute pressure measurement. You want to measure the same pressure with respect to atmosphere, 760 millimeter, 1 atmosphere, 760 millimeter. With that, we call it gauge pressure or relative pressure. And you don't want both. You want, I have P1 and P2. Your height is 5 feet 6 inch, 5 feet 7 inch. I want the difference only, not his. The differential pressure, what you want to measure P1, that is called differential pressure measurement. Now, I don't want this. With respect to you, I want some other persons. So, you are a reference. With respect to that, I want to measure some other P3 referenced. That means, we have 3 or 4 types of measurement. One is with respect to vacuum. You make a vacuum, apply the pressure. Whatever pressure you measure with respect to vacuum is called absolute pressure measurement. Not that. You want an atmosphere. Your blood pressure, what is our blood pressure? A normal human being, diastolic and systolic blood pressure. What is the blood pressure? 120/80. Exactly correct. 120/80. What is 120? What is 80? What is the unit you didn't tell me? Huh? Yeah, but what is the unit of the measurement? Millimeters of mercury. Yes. 120/80. Is it an absolute or relative or gauge pressure or differential pressure? What is that? See? Huh? Relative, yes. Exactly, it is with respect to atmosphere. Because our body, when there is a cut, it oozes out the blood, it won't go inside, no? So it is definitely, with respect to atmosphere, is a higher pressure. 120 or 80 systolic is more than the atmosphere. So that is the gauge pressure or relative pressure. Yes, you are correct. So we want to measure that. That is whatever you use for that measurement is a relative or gauge pressure measurement. Now the reference, I want a reference, with reference to that I want to measure pressure, that is called reference to pressure. I don't want both, I want to measure between P1 and P2 only the difference, like height difference, that is called the differential. Packaging, why I am explaining here, not because of pressure, the packaging for this, packaging for this, packaging for everything is different packaging. Simply you are going to see that some animation, how it is different. So we may say I have made a pressure sensor, but is it absolute? I don't know. Is it a gauge? I don't know. Is it differential? So by this, so you are going one step for your own, whatever you do, I am telling you, go deep into that, see that whether it is what's good. Now this is the technique what you use. These are the sensors used for space applications. We have all different type of pressure sensors. What you see for a launch vehicle like PSLV recently launched Monday night. So we use this type of sensors, about 120, 130 numbers of pressure sensors for each launch vehicle. Each weighs about 100 grams. So you think 100 sensors of 100 sensors of 100 grams. You think 100 into 100, how many kgs you get it? So 1000 or so, no 1000, 10,000. How many kgs? 10 kgs. 10 kg. If I make same thing in the sensor using the silicon, I can make in 10 grams. So 10 kg, if I make it 1 kg, I can, my propellant also I can reduce, means the loading of the propellant, nearly a ton or half a ton or something. Some crore rupees also we can save in the propellant, and also light vehicle can carry something more payload. This is only one example I am giving you, just an example. So like that you have to reduce the sensor dimensions, sensor weight, and you can really reduce the launch cost also, and also the cost of the sensor because of mass production. Okay, when you talk about sensor, when you're packaging, I want to tell you one thing. It is not just measurement of pressure and you compensate for temperature and all. By chance, a person takes the sensor to the launch anywhere and it goes like that with a wire. So if wire cuts, one case. So you have to see that even by chance one wire goes out, you should have a redundant things. Now, by chance a person when he connected the output of the sensor, he connected to the power supply, and the power supply, whatever the output has to come, he has connected to the power supply, and the power supply thing is connected to DVM. What will happen if you connect your laptop wherever the power connect somewhere, and so what may happen? There is a short circuit, something will happen. Output you are connecting to a power supply. What will happen? Output of amplifier you are connecting to power supply. So it will go. You interchange the power supply, positive, negative. Instead of that you interchange. Laptop you are very specific. You connect that it is always positive. Polarity is protected. Now you simply interchange. What may happen? What may happen? Interchange the power supply. What happens? How to know? All ICs. Any IC you take 741 or OPO7, interchange plus minus 15 volts, what will happen? It will work or no? It won't work. Okay. Now you have to protect it. That means you have reverse polarity protection. Even by chance you interconnect, nothing should happen to the sensor. So you have packaging you have to think of. Can I put a diode in the series? Yes, it is protecting the, because it is high cost when you package it. So you have to protect that. When I short circuit the output, nothing should happen. Can you protect it? Possible, no? You have fold back protection, you have so many protection you have studied, possible to do. So can you do that? Now the person, when you want to test that, he takes the sensor and hits it when he wants hit it somewhere, because he want to have equivalent to screw or something is not going. So if for example he hit it, so this may damage. So by that impact also should not damage. We are not telling you hit with the sensor, but I am telling you, so by mistake something happens, falls or somebody hits, nothing should happen. So all these packaging you have to think in handling, in packaging, short circuit, open circuit, EMI, EMC, all the time. So these sensors, what you are seeing, one sensor, what is going for our mainly the space mission, like even in Mars mission or Chandrayaan mission, this type of sensor is having all that protection. Short circuit, nothing should happen. If it's by chance you interchange the polarity, nothing should happen. By chance it falls, it is tested for vibration, shock, humidity, temperature and all that. Minus 42 plus 120. It tested for various vibration levels up to 13.5 G, random vibration and all that. That's what the packaging has to take care of. And whatever you see here is the conventional sense. What you have seen, this is for which is going for a satellite. This is going for launch vehicles called differential sensor, which measures the difference between two pressures. You have a sensor, I told you 100 grams, it's called a 21 NA type for absolute measurement. This is what around 100 used in each launch vehicle. You have 1 atmosphere to 330 atmosphere, different ranges. You have a level sensor, ultrasonic level sensor, wherein it measures which stops at a particular level, predetermined level, and gives a signal that yes, it is now it's full, and you can switch off. It switches off. So you have a ultrasonic level sensors. Not one, you should have two. By chance one fails, in even that case one fails, you should have one more. So you have this one. You have a temperature sensors, various temperature sensors. You have a flashdown sensor for our spacecraft recovery experiment. When it simply touches the water, the flotation system has to operate, and you have to lift the satellite system, and whatever zero gravity experiment, microgravity experiment, some experiment did on the space you want to see. So for that you have flotation. You have to see that the flashdown sensor works. Hydrogen depletion sensor. In any vehicle, if hydrogen depletes first, there may be a disaster. You don't want, like a fuel in your vehicle. When you go from here to Kharagpur to maybe city or railway station, you have only quarter liter of petrol in your car. Can you go to the city or Calcutta and come back? No. So you know, yes, I should have at least half a tank or full tank approximately. So the health monitoring of any vehicle is based on the propellant availability in the spacecraft or a launch vehicle. So that has to be determined. So in one case, we have to see that whether really it is depleting or not. I will be showing you a small, maybe it is there, I will see. You can see that one how the depletion works. Nothing but capacitance principle. If there is a dielectric R, you know, epsilon R is 1, dielectric constant. If there is a liquid hydrogen is 1.2. Simply if it is a liquid hydrogen not there, it becomes 1, and we connect in parallel, we see that yes, there is a change in the dielectric constant, so capacitance change, and the liquid is not there, switch off, something like that. If maybe there, I will show you that if it is there. So then a triple redundant level sense, there is a cryogenic capacitance type. Not one fails, one more, otherwise all things you take care of. So triple redundant. So many sensors are there, pressure, temperature, and level. And the pressure, when you reduce it to MEMS, it becomes only 10 to 15 grams. And the same specification or better than specification, but we have to see the reliability of that. So that's what even today Russians or Americans, they use conventional technology because its heritage is there from 20, 30, 40 years. For MEMS, have yes, some tests are going on. So we have to see that if it meets the complete reliability standards, then it goes. So when you go to MEMS, these are the MEMS devices. You have the MEMS Wheatstone bridge configuration on a diaphragm, and if you make a small hole on that, it becomes a flow sensor. You can make it like a venturi or like your orifice. You can measure the flow in that. You put on a silicon with a silicon oxide or silicon nitride, have a platinum meandering path, then it becomes a temperature sensor. You have interdigital things you can measure for level sensing, density, viscosity sensing. Of course, you can, what you use for the accelerometer, similar structure, one can use for the level sensing. Humidity sensing, I want to see humidity. You have a capacitor place in between some epoxy or some polyamide or something like that. If it absorbs the humidity, it changes its dielectric constant, and you get a change in the capacitance. You know the C equal to epsilon naught epsilon R by D by A. So you know A by D. So you know how it comes. So that one can use it. Then depending upon the requirement, you know Kalpana Chawla, you have a Kalpana Chawla center. What happened is the disaster, how it happened? Anybody can tell? Kalpana Chawla astronaut, what happened? While re-entry, what happened? Yes, yes. Not stop working. The high temperature is given away because you have silica tiles like that. So there is a gap and other things. No. So if the temperature exceeded beyond a certain limit and the gap is there and that is not properly covered, there is a possibility of going out. So can you detect such things in advance, not in the flight and all? In advance, take remedial actions. So in wind tunnel or shock tunnel, they put the sensors, and this is an array of pressure sensors, and then test in these nose cone or something like that. When you apply that re-entry conditions, what happens to even the small projections, or there is a cavities, what happens to that? So can you take a remedial action? We want a fine surface there, should not be any, those things. Yes, with the pressure studies, you can have an array of sensor because of MEMS. It's not possible conventional strain gauge you can put. The sensor is only 1 mm by 1 mm, and what we say gap is also in mm or microns. So you have to study that. For that also you have things. So these are some of the sensors what is used for the space. Some package of using MEMS, you see how small it is. One can use for commercial application. The small sensor itself is the size is reduced. I forgot to bring, otherwise I could have shown you. I could have brought us. These are the sensor on PCB. These are sensor what I told you going for the satellites and with all the protection circuitry. Even now they use it. It gives output of plus minus 5 volt for excitation of a plus minus 15 volts. And you have a MEMS sensor. How small it is? You know, it is again with the 5 volts you can get. What the Professor Lahiri has explained to you, it is not that MEMS, component of MEMS may not only the sensor, but sensor, actuator with the signal transduction circuit. This completely become microsystem. And the present day, the power supply also goes inside, like a thin film battery or RF source goes inside. So it becomes the component of MEMS, and the total together. That's why MEMS, micro electromagnetic systems, micro sensors, microelectronics, actuator, and structure together. You know that anything, any sensor or something like that, when you put on a header, we call this as a header because you have to interconnect it. You have a glass to metal ceiling. You will be seeing the next slide exactly how it looks like. And we wire bond each point, maybe a Wishbone bridge configuration, a open bridge. You wire bond it using a 1 mil wire, and then take the leads other side and apply pressure on this side. How it looks like, you will be seeing that. We can't apply directly the pressure, so we use the stainless steel diaphragms of different types depending upon the requirement, low pressure, high pressure and all. So what you see in this case is this is the diaphragm of stainless steel of 304L or equivalent austenitic steel, should withstand the corrosion or erosion of your liquids. So then we have to, like you saw DRI, you go to deep reactor, here we go electron beam welding. The width to depth ratio is very high. So depth you can go very high, like 1 mm, 2 mm, whereas the width is only 0.2, 0.3, 0.4 mm. You can go that by electron beam welding. And you see this, how it is being assembled. You can see here in one of the this animation. Even though the MEMS chip is only maybe less than 0.5 grams or so, 500 milligrams, how it is each the package cost increases. See, this is the simple chip. That's all, and it is bonded on. There is anodically bonded on a glass, and the chip will attach here, and gold wires will take. So you have a chip. You have some epoxy, you have a header with a glass to metal sealing, this is a metal, this is a glass, specific metal called co-variable, means it should have the temperature coefficient of expansion equivalent to the glass, and that's what you want to have. Gold plated wires, and then you have a chamber, stainless steel, a diaphragm, and this together will be electron welded. You will be seeing animation, and filling of the oil is done using a ball and screw mechanism. You see this in the next thing, how we do that actually. You have this header made up of a covar material, and you have the glass and the wires. After the glass metal sealing will be gold plated. You have the die, it is a die attached using the adhesive, like I told you, thermally conductive but electrically insulating. The wires wire bonded. Then you have a chamber, this, then on the chamber you put this diaphragm, and then go for a cap and then weld it each joint. It become a hermetically sealed connector. But inside you should have oil. How to fill the oil? Yes, you have this mechanism. You fill the oil, put a screw, ball and screw mechanism, tight it, and if required you can weld it also. It becomes a fully hermetically sealed. Whatever you wanted to measure the pressure, faithfully it acts on this diaphragm. We see on this diaphragm, faithfully it acts on the diaphragm. That diaphragm transmits the pressure to the basic MEMS chip, thinner diaphragm, and then you measure that. That's what the technique. So you know how the size is becomes so big. That's why 10, 20 grams. Even though 0.5 grams is this, but total thing becomes 20, 25 grams depending upon requirement. That's what I wanted just to show you that. So these are all the techniques which used, because I have to cover some of the things. Humidity sensor. I have shown you the humidity sensor works like a capacitance only, and how you do it. So these are the processes. I think Professor Somandas may explain you the each and every process, not on humidity sensor, but normal processes, how we are doing it. It is nothing but the electrodes are there, and in between you have a polymer. So that's what we do that. So this is the various processes which is there, and when you subject it to various humidity levels and see the output, when you convert using the capacitance converted into electric voltage, it may be non-linear. you can convert to linear. You know nowadays linearization technique, best fit straight line methods are there, curve fitting is there, you can make it straight. So all this output what you get is raw output can convert into a linear output, and you can have humidity sensing, temperature sensing. Yes, on a silicon you can have a silicon nitride or silicon oxide. Over that you can have a meandering pattern of platinum or titanium or some depending upon the requirement. Yes, platinum is there. For example, you want 100 ohms, yes, you can make it 100 ohms. Photolithographic technique, you can calculate and measure. R equal to rho L by A, you know that, isn't it? R equals rho L by A. Rho L you can decide, R you can modify, isn't it? Area and all that. So you can do that, rho L by using that you can define 100 ohms you want, 200. That's what you call it tailor-made films. 200 ohms, 1000 ohms, 2000 ohms, anything is possible. You can do that, and you can have pads here and take the lead out. For redundancy, you have pads like that, or 4-point measurement you want to do. Yes, you can have this 4-point measurement. You can have like this. So this is how. Why platinum is used? I think most of you know why platinum. Temperature sensing mostly used. Temperature coefficient, yes, one is thing 0.00385 ohms per ohms per distance. What else? Bonding is also okay, but it is an expensive material. Huh? High sensitivity. Okay, sensitivity is also okay. Then corrosion product, correct. Then it's a noble metal, isn't it? So corrosion. Then what else? Very important, stability. After 10 years, 20 years, 30 years, stable, nothing happens. You take copper, it also measures, but only one time, oxide coating and other things, and it won't. So the platinum found to be the best because long-term stability. Also, apart from all whatever you told. So now we have other sensors with the silicon. You can have a sun sensors, you can temperature sensors of, and this surface acoustic wave, magnetic field sensors, so many things, and everything stacked. You see, this is one of the European Space Agency photograph what I have taken from the ESA. So you can see how it is stacked. Wire technique is used, and multi-chip module is used, and all the technique they used for stacking the sensor, various sensors, not only one sensor, various sensors together. And their present pressure sensor is like that. For high pressure sensing, they use a different technique. They have it looks like cantilever, but it's a tubular structure wherein the strain gauges are outside. So this is what they use at present for more stability. Vehicle, many sensors are being used. You have seen many places, I think even in the YouTube or in your internet, seen a lot of sensors. Let it be the identification of if somebody steals the car, identification, then automatic toll connection, correct, even in Delhi they do know. The vehicle can simply move, toll is cut from your credit card, isn't it? So that's again, what is that? What is the technique used? RF MEMS. So accelerometers, then or gyros. Anywhere you go, you can find out Kundus, Dr. Paris Kundus place also you can find out where it is. You can go exactly that. So anything is possible. So a lot of chemical sensors, because you want to see is it a CO emission or CO2 emission or something, is it within the limit, all that. Smart door, seat, all that. Those things, everything is in 150 sensors now they are adding. Example, one sensor, we have a manifold absolute pressure sensor, or called this is mainly to measure the pressure in the engine and the automotive things, which is SCL and Precol designed together under NPMAS program. Now it is going for productionization. They tested a pressure sensor. We're having temperature also indication. They want it for the automotive application, mainly for mixture ratio control and other things. Now, can I use for biomedical application? How many people are diabetic? I don't know. How many, even I myself may be diabetic. So simply stand on an area of a pressure sensor. Your contour of your leg, the pressure contour, can give you whether you are diabetic or not, qualitatively, not quantitatively. It's possible to measure. Like acupressure you are talking, acupuncture you are talking. Can I have this technique? Yes. You have an area of pressure sensor, simply stand on that. For that, how to package it, the sensor. This is done in instrumentation department of Institute of Science, and MEMS sensors are used, oil filled and with a simple rubber on the top. So it measures that, and one can use for even for your comfort, for your house and even vehicles, vehicle seats and other things. Wall-less micropump, I think this already done even in IIT Kharagpur, and or Somandas Kundu is there, and Bidhan was there. So I think these are the sensors where without a peristaltic wall-less pump can operate, and you have a PZT on this diaphragm. So it operates depending on the frequency. It can suck and it can deliver without wall, and it is a very small size and low power. Maybe 5 volts it operates, and it gives you mainly for biomedical application as well as for when drug delivery, where you want to use for the applications where you want only few drops. So for that purpose. Of course, I forgot to bring one more slide. Such things, if you convert it to a peristatic pump, you can lift say 1 mm column of water to 12 meters or 13 meters with the 3 volts and 40 milliamps. 125 quarter watt of a power can lift a 1 mm or 2 mm column to 12 meters. That's what we have seen. Not in this type, but peristatic only, but with a tube. So of course, for helicopters, you know, the lot of accidents happening in the helicopter. Even that is even though disaster recently you saw in Uttarakhand also. So a lot of sensors they are planning. Even anything happens to that, well in advance if you are able to know. So can you take care of that? So a lot of sensors are there, including the temperature, pressure, speed, strain on the because of the wind or something, strain on the blades, all that, and everything, speed, including the speed and other things. So a lot of sensors are being used, all MEMS based sensors. I told you the rotating machinery like a Kaveri engine for our light combat aircraft or some aircraft, whenever you want to do. It is rotating in high speed and you want to measure the speed, you want to measure the strain or stress on the blades and the temperature, cavitation, everything. Yes, it's possible. Every sensor will be there, and through the your RF network you can get, or by optical also you can get. So there's a lot of, like you have combustion process sensing, turbine power plant sensing, you have wireless vibration sensing, all health monitoring, everything you can do that using that. So these are the things. Of course, the products are enormous. You can have a 3-axis MEMS. This is an old design. Now presently everything in a single chip is available for an accelerometer. Accelerometer is very nicely explained by Professor Lahiri. So with that, I want to tell you the scope is innumerable. I am giving some time for a discussion. So innumerable. You have the accelerometers and pressure sensors. At present, already defense is starting to use. Aerospace, health monitoring, accelerometers, shape memory, magnetoresistive, pressure sensors, and all that. Space, we are working on pressure sensors, optical gyros, propulsion system. Of course, the basic what I saw first, what Professor really explained you, the quartz thing, Somandas, and the quartz thing, what at present it has gone to in a way it can be used for the satellite application now. And we have seen one more application of this, whatever you have designed those days, can be used for tsunami sensing, which I am not covering here because that is out of the syllabus. So in tsunami, how many of you know what is tsunami? I am not talking Himalayan tsunami, actual tsunami, tide. What is Su? What is tsunami? Tsunami. Su is a harbor. Nami means wave. So harbor wave. So it goes to very high. Why it goes very high? So in 3,000, 4,000 meters below the ocean, there's a tectonic thing, and you have a small earthquake. Due to that, you know, 3,000 meters below means you have 300 bar pressure, 300 atmosphere of pressure. There, the small change is only 3 millibar pressure. Over 300 bar, 3 millibar, 0.003 you have to measure. So very, very accurately you have to measure. This sensor, even today, they use digiquartz, US. They use only the resonating quartz beam sensor is used because small delta F frequency change one can use for this measurement. Even today, they are using it. Very expensive. One sensor with this thing costs maybe few lakhs, because you should that is stability and the accuracy, and you can see the repeatability of the sensor and accurately to measure the 3 millibar over 300 bars of pressure. So very 3 to 4 millibar some pressure. So very accurate. So digiquartz is doing that. So this system will help. We have tried some of the system what has done with the ASU and last two when I was there. It is giving very good results. Something like 7 to 10 hertz per millibar we got. Very good output. So one can forward make it to use for tsunami application, this quartz thing. So that's one thing I want to tell you. Yes, it's possible to use for so many other applications, and even humidity sensing, other things. Okay. So you have the optical gyros, propulsion systems. I think okay, that you may show the your thrusters and other things. I may not show you that. So then airbags, tire pressures, fuel injection, drug infusion system, micro needles and all that. Lot of applications. These are the scope for packaging, electronics and other things. I have summarized then and there, but still I want to tell you it is possible to make, because you people are young and young professors and young students and researchers. It's possible to fabricate cheaper, smaller and lower cost. When China can do, why not India? Isn't it? You are getting low cost toys from China, isn't it? Whether we are getting the same cost toys in India, all automatic toys and other things. The MEMS is used extensively for toy in China and other places. Can you use it? Can you make it? I'm not telling you compete with them. I'm not telling that, but can you use it for that? So there is a power micro. So it is a lower power micro device for electronics to support various applications. I'm not talking about a toy here. So batch producer MEMS sensor like temperature, pressure, flow, acoustic, level, acceleration already available. Is already packaged for harsh environmental, already available. So can it to make it cheaper or better? Specification can improve. Packaging of devices like sensors and actuators depends on its application, and so is the cost. Automotive application cost maybe 50 to 100 rupees. Same sensor I can use for space. It may cost 70, 80,000 rupees because the packaging is different. Same basic sensor, pressure sensor, if I use for space, it will be different because it has to undergo vibration, shock, then your humidity, radiation levels, all these temperature, everything it has undergo, and you have to package such a way that is robust. That's what the packaging depends upon the application. Biomedical application. Can I use the sensor with like this? No. You have to make it a specific sensors so small and embedded and biocompatible. You can't use some of the things. Lead you cannot use. You can't use some of the even the whatever you are using, the epoxies. You cannot use cyanoacrylic epoxy. You cannot use. So how to do that? So those things. So that is the packaging depends upon mainly on the. You have to tell that depends on application. What is the application about it? Biomedical, process industry, only atmospheric, or some other use. See that. The functions of an electronic sensor package are to protect power. See, are to protect power and cool the microelectronic chips. This is important. I told you in the beginning itself what is packaging and what it means. I told you. So all this you have to take care of, and by that, yes, you can make one electrical and mechanical connection between sensor and electronic part and the outside world. That is very important. So of course, the current system technology like system on chip, multi-chip module, and the system in package. Apart from the, I am not talking about the wafer level chipset scale packaging is very important. Now it is becoming very, very famous. Wafer level chipset scale packaging. In the wafer level, everything you can do it. That one. Then you have a flip chip or plastic ball grid array. That is the latest techniques, which is yet to be qualified for some of the major strategic applications. These are things. So currently, for people to go for, if they are interested, you can go for these things like wafer level chipset scale packaging, or which I am not covering here. So with this, I will stop at this point. You have references. Everywhere I have given the references so that you can refer, and also some of the books, including the packaging course what I am teaching, and the instrumentation book, Rao Tumala, fundamentals of microsystem packaging. Then this Samir and PRC one, Georgia, Atlanta. Then Thairansu. These are the references. With this, let me stop here, and any questions? I think I have some time for question and answer.
So like in surface micromachining technique, like whenever we design a membrane, like for say example a 6 feet, can we design one membrane and one over it, like a stacked structure?
Yes.
Like is it standard?
Yeah. It is there. I think when Professor Soman asked me explain you, that is there. You can do that. Yes. Only technique how you do, process how you do, that is important. Is it one over, or you will go in a different pillars for that, how you use it, that is important. You can do it. There are ways to do it. Only the when you process it, the process how you do it is important. That he will tell you how the sacrificial can be removed. One you remove first, then second one, or both at a time you want to remove. How to do that? Yeah, this is done.
They can be like two different.
Yes. This is done. Of course, there is one research also going on a double diaphragm pressure sensor using that technique, two diaphragm technique. So it's being done, and different stages. One is lower diameter, higher diameter, and lower diameters. Yes.
Suppose if we talk about MEMS switches, now in that we have coplanar waveguides, but in the external environment we usually have cables. How do they integrate in the packaging type
Yeah.
from waveguides to cables?
Right. See, you have seen any one RF MEMS how it is connected? Yeah. See, you have a yes, this is a very good question. See, RF will always have a problem, and it is always the bonding. What I told you, bonder cannot use. It's a deep wire bonder. If you go to SL Chandigarh or you go to Delhi IIT with the Professor Shubhan Kaul's lab, you see a little different. The RF MEMS is actually packaged in a different way. Even the substrate you have to see, because your all RF things depends on the substrate characteristic also, isn't it, a dielectric constant. So once you have designed your MEMS, your pad size should be thicker than the normal things, because what they do after wire bonding, you solder that one to the micro dot connectors. It's a coaxial connectors called micro dot, not big connectors like BNC connector what we have in the oscilloscope. So micro dot connectors almost 1.5 to 2 mm connectors with the center this thing exactly like BNC connector, but the center and outside you have that shielding property. You have to solder it there. So that cannot be done by the wire bonding. But now this same technique can be used using a ribbon bonding. They use a ribbon. Instead of wire, there is a ribbon. Ribbon will be bonded by the similar machines. You use the ribbon bonding. Ribbon is about 1 mm, different, little thicker and little wider than the normal wire. So about 0.5 mm, 1 mm and all available. So you have the ribbon of copper, or you have aluminum, mainly the copper. You can bond it or solder it. It is possible. So what is known as a parallel gap welder. Hughes makes a parallel gap welder. You can use those welders, and these whatever the your connector pin, micro dot connector pin is there. You can place this and weld it. It's a parallel gap welder. Simply give some voltage, and it welds at a single shot, comes out. And manually is possible. You simply leg with the pedal. This parallel gap welder goes there, heats the surface, melts it, joins that, comes out. Single shot. There is a capacitor charging and then discharging through this short circuit. It heats up and then joins. It's possible to do that. Only the tip or the fixtures, tools you have to design to suit your requirement. You can go to Hyderabad and Astra Microwave. I think they also do similar work. A lot of work is being done in Hyderabad. You can see that also.
So we talk about hermetic and non-hermetic
Yeah.
backward packaging.
Yes.
So can you please tell me the basic difference between these two?
Hermetic. What is hermetic? Why the name has come hermetic? Isolated. Yes. Hermit, the sannyasi, or the who call the person who. So he's away, worldly things are not there. So hermetic came like that. So here, the external world, for example, I have hermetic seal. Whatever happening here, this atmosphere, one atmosphere, is not going inside. So it is completely sealed. Nothing is seen by whatever happening here. Heavy rain, no, inside is paka, same. No rain, nothing. Vacuum is vacuum only. If there is a pressure, same only. There are high temperatures. There may be change, but not too much change in that. But mainly the pressure variation, nothing will happen to that. Now, when you want to do that, you have to use specific machines. I want to use this welding, what I told you, the hermetically sealed, what I want is a vacuum. I can't use a normal TIG welding, MIG welding and all, because it is atmosphere you are doing. What we do is electron beam welding, where the complete chamber is evacuated to the 10 to the power minus 4, minus 5 torr, have two things apart initially, everywhere you create vacuum, using a solenoid valve, bring that together here, then weld it. Everything under vacuum. When you weld it, then inside is vacuum, you weld it, you take it out now, inside is always vacuum because it's nicely welded. How you know it's welded, is it really vacuum or not? Now pressure sensor we have put inside, for example. See, previously it was in atmosphere. Let me say it shows you zero output reading. All the bridges are balanced at zero. When I put inside and evacuate it, what happens to the diaphragm? Previously it was like that. Now because I evacuated it, other side is maybe atmosphere, it bends like, it either bends like this or bends like this. So you get an output. With that output you can know, yes, it is a vacuum is there inside or not. Then there is what is known as a helium leak detector, mass spectrometer. So you can evacuate the welded joint and check with the helium. You inject the helium, Helium, you know, why helium is used? Inert gas and then lightest. So it can go to any cavity, any holes, you get an indication, yes, there is a leak. We want for space application something like 10 to the power -7, -8 standard cc per second, that level leak rate is required. So we see every welded joint, every braced joint where you want hermeticity, we check for the helium leak detection. So then you know that yes, it is hermetically sealed. Non-hermetically sealed, these are non-hermetically sealed. If you put in water, water goes inside. Hermetic sealed one, if I put there, no water will go inside. You can atmosphere change outside, you have 5 bar, 6 bar, nothing. Inside is a vacuum, means vacuum only. They call hermetic sealed. And there are so many other specifications. Electrical connector you want to bring out, it has to withstand say 200 bar pressure, 300. We pressurize the system, see that it withstands 100, 200 bar pressure. Your good question, the worst case analysis means if I have to design a pressure sensor, it is for 10 bar atmosphere. For example, sensor is for 10 bar, I will test this for 20 bar pressure, nothing should happen. By chance, 10 bar becomes 13, 14 bar, it has to saturate and I should know, yes, output is saturated. That means I am going higher value, stop the pressurization or do some remedial action. Even the system fails, the pressure sensor should not fail. In any of our normal design is worst case, there is explosion happens, okay, pressure gone beyond certain limit. Oh, the sensor should not fail. It has to tell me why that explosion happened, what is the pressure went. Temperature sensor has to tell me what temperature, even though temperature sensor for 600 degrees centigrade, temperature went to 1000, it should tell me it has gone beyond 600, maybe 800 up to that linear, afterwards it may be non-linear or saturated, it should show me yes, temperature exceeded, that's why it is failed. So the design of a sensor should be such that worst case 1.5 times or 2 times it should be able to at least measure, not that accurately, but it should measure to a certain extent, tell us yes, pressure has gone high, temperature has gone high, acceleration has gone high, something like that. So depending upon the requirement, you have to design.
So if we can maintain vacuum within that device, within the packaging, then why do we give stress to the materials which are anti-corrosive or which can handle such harsh environments? Then there's no need of
No. If I go back, you'll be seeing that. See, you want to measure the, for example, we'll simply talk of your vehicle. Some vehicle, you have a fuel, petrol or diesel. How you measure the diesel pressure, tank pressure? How you measure? How you measure? That diesel should be come in contact with the diaphragm, no, or some tube or something. No, if it comes directly contact with the silicon or aluminum or there is a epoxy, some epoxy. You know, people will use petrol. If you have some this thing, you will use petrol and clean nicely. It cleans. So even the epoxy will, in some epoxy will melt in petrol or diesel petrol. So if you use now your pressure sensor of MEMS directly, the chip will come about and this will be separate and everything. Like our hand, leg part, everything will become separate. You cannot use. So it will simply open out. So you have to use some barrier which is not reacting with the petrol or diesel or acid or something like that. So I use a stainless steel which is compatible with the petrol, like stainless steel 304L. There is a quality. I can't use all the stainless steel. Some specific stainless steel, the low carbon steels I have to use. I use that austenitic stainless steel. When I use it, anytime you do this, nothing happens to that. No corrosion, no erosion, nothing. It won't. Now you have to faithfully transmit this pressure to the MEMS chip. So how to transmit faithfully? You should have incompressible fluid you want. So use a oil, silicone oil for example, use it. So it faithfully transmits. No doubt when you fill the oil, there should not be any air bubbles. See, if there is air is there, it itself will take care of, the cushioning effect, damps down and accuracy will reduce. So you have to see that the completely air is removed under vacuum system, then fill the oil under vacuum, there are no micro bubbles or something like that, then you see that yes, faithfully this pressure transmit to that. And oil should not come out after 1 year, 2 years, 3 years. Oil should be hermetically sealed. Oil is oil, there inside only, it won't come out. So it's hermetically sealed. So that's how for corrosive media we use this oil filling technique. You don't want corrosive media only atmospheric. Simply give a coating of some epoxy. You can use for atmospheric. You want only want to measure some conventional gas, argon, nitrogen, not required. But the wires, what I told you, the wires which is coming out from this thing, these wires has to be protected. See, when the pressure is applied, if the wire is like this, okay, think it's very small. But when the pressure is applied, this also goes down, goes up and down. No, what happens after some time? You go on doing like this always. What will happen? It will break. Similarly, when 1,000 cycles, 2,000 it may break. So we give a protection coating on these wires. Wires are not allowed to move, and not on the diaphragm, but on the only wires everywhere, so that it will be protected. So even when you go up and down, nothing will happen to the wire. Wire won't move it. Some of the places where it is not, you don't want to do that way, so you have to think also. Little bit, general knowledge also helps here. So that's what I want to show you here, specifically on one place. Maybe. I can't stop, but I'll tell you here. See here. You have this, and these are the glass beads and glass, and this is a core. Now see this MEMS chip comes and we attach with an epoxy, thermally conductive electric insulating. These wires, no. If I keep wires like that open, you have seen the wires. If I put oil and all also, because of the oil going up and down, maybe a few microns, but the wire also goes up and down. So what we do, which I have not shown you, if I cover you can't see. So we put on that one epoxy called an NPR 100. We put it, so it will be protected, and also it is stuck to the base. It's electrically non-conductive, it's insulating, and thermally conductive epoxy we put it. Then we do that. That's why. If time is there, I can show you the real cross section, what we have done now, but I don't know whether I have that much. One, you can see the real 3D cross section if possible. 3D. Maybe you will see. There is a 3D animation, but I don't know. No, you're not able to do that. Go back. Now, see, this is how the assembly takes place in a 3D config. You have a diaphragm which is comes there, and we weld it, and we put this ball and screw and the oil filling and all. I'm not showing here. Then you see this is your wafer, that whatever the die is attached, of course, with the glass to this metal ceiling. Now you may be able to see, or I don't know. We'll see. And this is attached using an epoxy. See this area, just to give you an idea. So this is attached using an epoxy, and wire bond. Wire bonding you are not able to see. See the cover. What you see, that flat thing has come. Is nothing but covering of an epoxy on that. So that's what we do. Then we put all this become a capsule. We oil filled everything is become a capsule. Then electronics comes in this. So this is a PCB, which is bigger than this. You see PCB. You should have EMI protection. You have a back-to-back diodes, power supply protection, and you should have a output protection. Everything. Then put a connector there, and then weld it. All that. So even the sensor is so small, you can see how big it is. It becomes almost this big size, and fully protected, hermetically sealed. Nothing happens to that. So that's how this is done. Just to give you an idea, because you asked that question, so I thought, okay, I'll show you that. And you can see that each and everything you have to take care of in the beginning. How we do this diaphragm, how will the diaphragm to be attached, what is the dimension in microns level, and how you put this die here, and how you attach the die and this, how you weld this joint by electron, and how you put this ball, and what is the dimension. This is only 2 mm, 1 mm ball and 2 mm length thread. M2 into 0.4, and how you do is how you weld it, you take care of this, how you put a PCB inside, how you wire it, and how you pot it, this one, and how you put a connector with the ring, because connector cannot sit directly, how you put a connector there, electric connector, and take these leads out from the connectors. Everything has to be taken in advance. Our actually aim is to only the sensor, but to make it working for some specific purpose, you have to take care of all this. Just to give you an idea, it was not there because you ask a specific questions. I'm putting it. Now this sensor, even if you drop it, nothing should happen. You vibrate it 13.5 G, very high vibration levels, nothing should happen. No output should come. Even you give a shock, you drop it, nothing should happen. So that is the philosophy. And somebody will tamper it or something. Output is short circuit. EMI EMC 461C RF, that high frequency you give it. So we have put EMI filters between the power supply and the ground, and also output and ground. See, EMI can pass through the power supply also. There are three types of electromagnetic interference. It can be conducting, susceptibility, electromagnetic, and radiation. All these three, CS it is called CSCR, something like that. All that in 461 mil standard. Very, very important. It may work as a sensor, but when you have a nearby some water is running, you should not give some output due to that. Or tube light is having a choke. Choke automatically, when you switch on, it gives high voltage, no? So it should not. All this you have to take care of when you design things. So you have to see the worst case scenario, worst case analysis. Not only that, because you ask a specific question, I am telling you one more point here. You have to see that any resistor or component, whatever you used, is properly chosen. If I have, for example, half a watt resistor, I cannot load it to half a watt. I have to derate to 50%. I will go only for half of that. Quarter watt, half a watt, I will go to quarter watt only. A transistor, which is or a diode, for example, PIV of a diode is 100 volts. I cannot use for 100 volts. I use only 50 volts because I don't know any time the sudden peak due to a solar flare or due to some lightning. Voltage may go up. That's why your TV is that, this will go no, because your protection is. So when protection is given, you should give 100% protection. We say derating of the component. You have to derate the component. You have to do worst case analysis. You see the reliability of the complete system reliability you have to see. Then only you have to do it. Which I am not covering. It's a 4 classes of reliability analysis. And there is a MTTF, that is called a mean time between failures. You have to see when it fails. We make not 1 or 2. You have to make 10 or 20 numbers. See whether all are repeating the same with the temperature, pressure, vibration, shock, and all that. And we have to aging it. Aging you have to do. You have to simply keep what happens after 1 month, 2 months, 3 months. After 1 year, it has to show the same output what is shown today. Is it possible or not? Then only I say it's reliable. That's all. So many things are there which I am not able to cover. You have to do a lot of qualification test, acceptance test, and do it. Even though 10 bar, I will apply 15 bar and see how is that. 15 bar I will give 10 times. Even though it has to withstand 100 degrees centigrade, I will go to 140 degrees temperature and see what happens. It need not work on 140, but I will see what happens. Whether it deteriorates the performance or low temperature, I have to go minus 40, plus I will go to minus 60 temperature. See what happens. Minus 40 sufficient, I say no, I will go to minus 60. All these, let's take care of. So these are the things what I thought I will cover. And any more questions? LTCC. I cannot explain. That is, that you have to go to CMET Pune or somebody here who is experienced there. Pathak. You can write. I am not an expert on LTCC or HTCC. So low temperature co-fired ceramics. So there is a Pathak is there. Girish Pathak from CMET Pune. If you give your email ID, I will pass it on to him. He will give you all details on. And it's available in the internet, beautifully given, all LTCs. And you can, if you are very much, you are from which place? Aurangabad, go to Pune, very close by. Pune, CMET, you go, Girish, full facilities available. You can see how the LTC is fabric. And there's the same whatever packaging is done in LTCC, how they do the packaging and how they go for space, defense, and commercial application they do, you can see. Girish Pathak. They have international conference, you can attend that. Yes, you IEEE+. Why not you attend? Then you will get a lot of. He's giving a talk, and he'll be telling about LTCC. Okay? Yeah. What is it? Depends upon requirement. I told. See, for example, you want a catheter tip sensor. maybe pressure sensor or temperature sensor or a camera. 1 mm by 1 mm, that's what. Less than, see, catheter, I can't put a catheter of this one to, isn't it? So, smaller, no, that's not painless surgery. Okay, I forgot to put some of the things because of time. Now people don't want pain, no? You have to go and come out without any pain. So, can you have a painless drug delivery system? Yes. Using MEMS, we have micro needles of 100 micron diameter outside. Inside is only 60 micron. Total length is 1 mm to 2 mm. Even if you put here the patch, you won't get pain at all. That is what one thing is. The patch 4 by 4 or 5 by 5 matrix of micro needles, which I have not shown you. And that is this insulin is injected through a small micro pump and it goes inside. Without your knowledge, it can go on giving 140 microliters bolus dose when you want. Otherwise, it can give 140 microliter, 100 microliter, depending upon your requirement. It can go on giving for a diabetic patient. This is one thing. Dentist, for example, you have a, I forgot to show you. The dentist, he gives you an injection for remove extraction of your teeth, isn't it? Painful or not? No, painless. You can have a shock tube. Simply keep here, shock tube, and shock. Through shock, that same anesthetic drug is gone to your gum, become anesthetic, you can remove without any pain. So with the shock tube, Professor Jagdish of Indians of Science, they have done some studies, similar things. Bamboo, preservative is very important. Bamboo is, simply it is vanishing. So you can, preservative can be done by the shock. If you give injection, very difficult, 40%. So with the bamboo preservative done by that. Then cleaning of the silicon wafers and all that. You can create a small tsunami inside the lab by giving a shock, all that. So you can do that. So the extraction of sandalwood oil, very difficult to get the sandalwood oil when you extract normally, like a sugarcane juice. If you give a shock, 80% to 90% oil can be extracted. These are the things are possible. So many things you can think, there is actually no limit. Depending upon the requirement, if it's 100 mega, 100 mega, if it's a catheter tip sensor, 1 mm by 1 mm catheter size, 1 mm catheter diameter, okay. But if it is a space, that 1 mm will become 25 mm for me because all this PCB is big, my header is big, everything that what you have seen is so big and diameter is 1 inch, 25 mm diameter, very big. If it is for automotive, it is about 10 mm by 10 mm by plastic package, what I shown you. Same thing only, same sensor, but packaging is different. So same sensor for intracardial pressure sensing or for catheter, for space, for defense, all that is different. Size depends on how you choose. If you want, you can make it 1 mm, 1 mm, or you may 2 mm, depending upon the requirement. You can choose.
I think.
Yeah, tell me one last question. Okay.